So, good evening to all. You are able to hear me, all of you confirm once. Right. So, in my last class, I have given one numerical to solve. So, I can see one or two have given the reply 52.38 Newton meter. Right. So, let me continue. Right. So, I'll continue the class. See, Baba, one thing. See, I have given when does class start just now. See, I gave my sir. Some people have exam on July 18th, IAS exam, right? See, you can speak to the concerned manager. Then accordingly, whether we can have class or the class can be cancelled. We'll see, right? See, anonymous attendee. Sir, you are starting the class late and ending earlier. What nonsense you are talking. See, I have started the class at 5:11 and I am ending the class at 9:10 or 9:20, sometimes 9:30. My schedule hour is 9 p.m. Right? I'm ending at 9:30 or 9:15 around that. You are not supposed to talk about the timings. I know when to start and when to end. So it is not a physical class. Last class and today I was late. So better you mind your work and try to ask the questions related to the subject, not related to the timings. Right, 52.38 Newton meter is the correct answer. Fine. See, most of the SEM exams also there. See, Baba, I can understand all these things, SEM exams and other things. So I think you are having the schedule manager number, so you can speak to them. So accordingly, you can just, right? Please remember that. Please remember that. See, I gave my number to ask the valid questions. But very unfortunate thing is, for simple thing, they are just sending, sir, how it is, why it is, can you please send the answer? See, if I'm correct, you are in final year, some of you, or some of you might have completed your graduation. See, one of the student wrote, sir, why omega r is equal to 2 pi n r by 60? So how come it is? Sir, why, sir? See, what is the meaning of why? I don't understand. So here, you know that nr is the rotor speed in RPM. A rotor speed in RPM. So whereas omega r, the rotor speed in radians per second. Then I convert that nr, which is in RPM, into radians per second. How? So nr is a revolution per minute. If I divide with 60, I'll get revolutions per second. Then in one revolution, what is the how many radians? You'll complete 2 pi. So it is 2 pi nr by 60. So nr is the rotor speed in revolutions per minute, whereas omega r is the rotor speed in radians per second. So there was a question on this, sir, why this is? Why it is? See, for that, what is the answer I can give? Please, you try to understand that. And one more student told that, sir, whenever the load on the motor is increased, you told that the flux in the air gap is decreasing. How, sir? See, this was already explained. So during one of the doubt question, see, if you remember, if this is the resultant field, which is rotating with ns, this is the EMF that is induced in the rotor winding, then this is the rotor current, a rotor current, which lags the EMF by an angle theta 2. So because of this rotor current, we are having the secondary flux phi 2. So what is the component of this here? It is phi 2 sine theta 2. Sine theta 2. So this theta 2. So again you will ask how it is, sir. If this is A, this is theta, this is A cos theta. If this is the vector and this is theta, so it is a cos theta. Similarly, because of this I2, there is one flux phi 2. What is the component here? It is phi 2 sine theta 2, right? Then theta 2 is equal to how much? Theta 2 is equal to tan inverse of S x2 naught by R2. So reactance part by resistance part. So S is equal to Ns minus Nr by Ns. So whenever the load on the motor is increased, then immediately what happened to the speed decreases. When speed decreases, what happened to the slip increases. When slip increases, the current drawn will increase. At the same time, what happened to this theta 2 will also increases. When theta 2 is increasing, what happened to this component phi 2 sine theta 2 will also increases. And you can see this is exactly opposite to that phi r. When phi 2 sine theta 2 is increasing, the flux which is opposing the main flux will try to increase. Then obviously what happened to the flux in the air gap decreases. What happened to E1 decreases. What happened to V minus E1 increases. The current drawn will increase. The power drawn will increase, and hence the power fed to the rotor will increase and the torque will increase. So this was already explained during the doubt clarification session. So it was already explained to you people. But still one of the student was asking, sir, how come it is? See, when the content is already explained, you are not supposed to again ask the same thing. And one more thing, one student was telling, sir, you told that the rotor will rotate in the same direction as the field. It is not the question of I am telling. It is not the question of I told that. So it was already proved using some law. It is already shown using some magnetic field arrangement. And it is very much clear that the rotor always try to rotate in the same direction as the magnetic field. Conditions apply when you are giving the excitation to the stator winding, where the rotor windings are short circuited. One of the student has shared one pic. Sir, you told that the rotor will rotate in the same direction as the field, but here the rotor is rotating in opposite direction. So it is not the question of my will, or it is not I am telling. So it is the law, it is the theory which is telling. And in that, the question is the excitation is given to the rotor winding with the stator winding short circuited. And this already I told you to one of the student. See, so this you can analyze. And I told you that this I am going to explain at the end. And I told you on that day. So please remember as of now, if you need the answer. So in this particular case, inverted fed induction motor, when you are giving the excitation to the rotor circuit, with the stator winding short circuited, then the rotor will rotate in a direction opposite to that magnetic field. I think this was already explained. Please confirm, raise the hands, all of you. Right. See, Baba, one thing, if you just ask some valid questions, some typical questions which you are not able to understand, then I have no issue in that. I can tell. Why? Because the reason for giving the number is to help you out to solve the things which you don't know. But it is not the funny and it is not the simple questions. Sir has given the number, we can throw whatever we want. You cannot. So please remember that and try to ask some valid questions. Valid. Then I'm there to answer. Right. And one more thing, better you mind your work regarding the timing. I know. See, my intention is not to waste your time. Even yesterday, day before, when there was no power, I don't want to miss your class. I know what are the alternatives I have done for you. Right, please mind. And I'm not leaving any class earlier. I was taking the class up to 9:15 minimum daily, but my scheduled class is up to 9. So there is some limitation for everything. You better in your limit. Your limit is to raise the questions, to ask the questions, to know the answers. Up to that you have the right, but no other right you are having. Right. So shall I start the class? Right. No need to, sorry, anonymous attendee. See, such something, a teacher will get distracted. So when such questions, see, even now also, I'm having a technical issue. I was like getting sweating. Why? Because if something has happened to me, happened to the class, my students are going to suffer. So I know that. Why? Because I don't want to kill your time. I don't want to waste your time. It is my responsibility that I have to feed the subject to you. Anyhow, we'll start. So no need anonymous attendee, sorry. So anyhow, please. Fine, Baba. I'll come back. So I'll into the subject. Fine. Right. So I think in my last class, I gave one numerical. See, so you have disturbed my mood, right? Anyhow, I'll come back. See, if anyone questions you, if anyone questions you, Are Baba, you are having, and one more question. One student was asking, Sir, electromagnetic torque is similar to full load torque. See, Baba, it is not a similar. Electromagnetic torque is the torque which is driving the rotor. And that electromagnetic torque is equal to full load torque when the windings are carrying the rated current and rated voltage. So, whatever the name we are giving to that motor, at full load is called full load torque. It is not different torque. Whatever the equation we have derived, it is only for full load. It is for electromagnetic torque. Remember that. Anyhow, I'll start. Fine. So can I proceed? Please raise the hand once. Can I? Right. Fine. So these concepts are clear, which I have explained to you now on the board. Is it clear? Right. Is this concept clear? Once again, raise. So why that with the increase in the load, all of you raise the hands. Why with the increase in the load, that so-called as flux will oppose, or flux will decrease? Please raise the hands, all of you once. I'll proceed. See what happened. So is it clear? My audio, video, and other things are clear. No one is raising hands. Clear. Okay, fine. Fine. See, don't ask any questions about that back EMF again. See, it is already explained. I'm just once again finally repeating before I proceed. Whenever you are increasing the load on the motor, then immediately what happened to the speed? Speed decreases. When speed decreases, then obviously I told you the relative speed increases. When relative speed increases, obviously the flux cuttings will increase. When flux cuttings increases, obviously the EMF induced in the rotor conductors will increase. The currents will increase. The magnitude of phi 2 will increase, and opposition to the main field will increase. You can see here, this is the resultant field. This is I2. So whenever you are increasing the load, this angle will also increase. This I2 magnitude will increase. At the same time, phi 2 sine theta 2 will increase. Then opposition to the main field will increase. Flux in the air gap will decrease. E1 will decrease. V minus E1 will increase. Current drawn will increase. Power drawn will increase. And power fed to the rotor will increase. Torque will increase. Is this point clear? Confirm me, all of you. Confirm me, all of you. Raise the hands. Right. Now let us proceed. Fine. So in my last class, I gave one numerical. Let us solve that numerical also. So most of you have given the answer. Very good. Excellent. See, the only twist in that numerical is the given voltage. What is that given voltage? VL is given as 240 volts. That is the only twist in the numerical. Most of the students feel that the given 240 is a phase voltage. Why? Because you know that numerically in India, the phase voltage will be ranging from 230 to 240 volts. You feel that the given voltage is a phase voltage, but it is not true. The reason is, whenever the terminology three phase is given, three phase voltage is given. So I told you that unless and until specified, the given voltage is a line voltage. So I'll write a three phase voltage unless specified is a line voltage. Unless specified is a line voltage. But in all our calculations, we need phase voltage. Now the question comes, why we need a phase voltage? The reason is, we are using impedance. When we are using impedance, what is the definition for impedance? Is it is the ratio of voltage phasor to current phasor. So whenever you are using impedance, then obviously that voltage should be a phase voltage and that current should be a phase current, right? So that is the reason in all our calculations, very compulsorily, we need a phase voltage for sure. So if I want to know the phase voltage, then you have to look into the given numerical, whether the three phase windings are connected in star or delta. So generally the three phase winding connections will be given in any numerical. In this, the three phase windings are connected in star, but sometimes say, so the data is missing, whether the windings are connected in star or delta, then in that case, you have to assume that the windings are connected in star and you have to proceed. But in gate, no such options will be given to you. Why? Because definitely the three phase winding connections has to be given for sure. So here, the three phase windings are given as star connected. Then what will be the per phase voltage here? The per phase voltage is equal to 240 by root 3. So what is it? 240 by root 3, if I am correct, 138.56 volts, if I am correct. Then here there is no information about stator impedance. As there is no information about stator impedance, then your E1 per phase is always equal to V1 per phase. So it is 138.56 volts. You can rectify if I am wrong, right? Done. Then what is the turns ratio given? 1.8. Then what is the value of E2 naught? E2 naught is equal to E1 by A, that is 138.56 by 1.8, so it is 76.98 volts. 98 volts, is it correct? E2 not 78.98 volts, is it correct? Right, done. Now I'm done with this E2 not. Then what is the value of the rotor impedance at standstill given? The rotor impedance at standstill is given as 0.12 plus j 0.85 ohms per phase. So if I'm going to compare this R2 plus j x2 naught, so what is the value of R2? R2 is equal to 0.12 ohms and x2 naught is equal to 0.85 ohms. 0.85 ohms. Then how many pole machine it is? So it is 6 pole machine excited with 50 hertz supply. Then what is the value of NS? NS is equal to 1000 RPM. Then it is given that the full load slip as 4%. That means when the motor is operating with a slip of 4%, the windings are carrying the rated current. So it is 0.04, right? Then anything is left? No. Then I need to calculate the full load torque. So what is the equation for full load torque? It is 180 by 2 pi ns SFL E2 naught square into R2 by R2 square plus SFL X2 naught whole square. So this is equal to 180 by 2 pi into 1000 into 0.04 into 76.98 square into 0.12 by 0.12 square plus 0.04 into 0.85 square. If you simplify this, it is 52.38 Newton meter. I think you got this answer. All of you confirm me. Raise the hands if it is clear. Right. Very good, Bob. So this is one. So if anyone questions you, as of now, if anyone questions you, are the rotor circuit parameters are given to you? Yes. The full load slip is given to you? Yes. So can you please find out the full load torque of that motor? Yes. Then, so whatever the example we have taken for that motor, what is the full load torque? Means 52.38 Newton meter. So this is one performance parameter. Next performance parameter is maximum torque. Maximum torque. Next performance maximum torque. It is also called as breakdown torque. It is also called as pull out torque. It is also called as stalling, means stopping. Stalling torque. It is also called as peak torque. These are the names by which I can call this torque. Peak torque. Peak torque. Now let me explain what is this peak torque. First, let me define what is called as peak torque. After that, I'll try to explain what is the difference we are having between. Sir, can you please explain A? Say it A. It is already given, ma. So in the previous numerical, you can see. So day 14, you can see. Just. So A is the turns ratio. What is that A given? You can see here. Stator to rotor turns ratio is given as 1.8. Anusha, is it clear, ma? It is given. So just like in case of your transformer, A is the ratio of primary turns to secondary turn. Here, A is defined as the ratio of stator turn to rotor turns. It is given as 1.8, right? Anusha, is it clear, ma? It is not taken, it is given in the numerical. I hope you have not seen that numerical. Please confirm me, ma, Anusha. Is it clear? Right, done, ma. Maximum torque, pull out torque or stalling torque. Now first what I'll try to do means, I'll try to explain what is called this maximum torque or pull out torque. After that we'll see what is the difference we are having between full load torque and maximum torque. So in my last class, when I was asking about the definition for full load torque, some of the students have given the maximum torque. See, full load torque cannot be always equal to the maximum torque. So let me explain what is called as maximum torque. After that, how it is different from your full load torque, I'll explain, right? Please see. If anyone questions, or what is that you have calculated as of now for your design motor? Yes, what is that? We have designed one motor, correct? So what are the motor parameters? R2 is equal to 0.12 ohm, X2 naught is equal to 0.85 ohms. The number of poles are 6. The stator to rotor turns ratio is 1.8 and the stator windings are connected in star. So this is the motor which we have designed. To this motor, when I am giving a 240 volts, 50 hertz supply, then we have calculated that this motor is developing a torque of 52.38 Newton meter when the slip is 4%, and we are calling that torque as full load torque. That is a different issue. So this motor is having a torque magnitude 52.38 when it is operating at a slip of 0.04, right? Is it clear? Confirm me all of you. Right. Now I don't want this torque. I don't want this torque. I need whatever the motor you have designed. Yes, this is the motor which I have designed with these parameters. R2 is equal to 0.12, X2 naught is equal to 0.85, poles is equal to 6, the turns ratio and this excitation. I want to know that motor with these excitations in the range 0 to 1, in the range 0 to 1, what is the highest value of torque the motor can develop? Once again, I repeat, we have designed one induction motor. When that induction motor is excited with 240 volts and 50 hertz supply, so it is seen that it is developing 52.38 Newton meter when the slip is 4%. When the slip is 4%. But I don't want this value. I want whatever the motor you have designed with the excitation parameters 240 volts and 50 hertz, how much maximum torque it develops in the range 0 to 1. That means this motor, what is the value of maximum torque it is going to develop with that excitation and with that design parameter. For that, what I will do means, I'll take this torque equation. What is the torque equation? I'll take this torque equation, general equation for any value of slip, that is 180 by 2 pi ns s E2 naught square into R2 by R2 square plus S x2 naught whole square. Then I'll substitute all the values of this motor in that equation. What are those all the values? So it is 180 by 2 pi. What is the value of ns? 1000. Here S is unknown. Yes. So what is the value of E2 naught for machine? 6.98 square into 0.12 by 0.12 square plus S into 0.85 square. So what is the variable in this equation means slip. So what is that I need to do? This motor with the excitation parameters of 240 volts at 50 hertz in the range 0 to 1, what is the highest value of torque the motor can develop? So for that, what I will do means I'll take S on one side, and for that S, I calculate the torque in Newton meters on other side. I'll start with S is equal to 0 and substitute that S there, 0. Like that, I calculate for 0.03, 40.6, 0.04, 52.38. Like this, 0.13, some rough value I'm talking, it is not exact, some 98. For 0.14, some 99, some rough values, please remember. 0.15, some 97, and when slip is 1, 27.64. So literally I'm taking S and substituting that S in this equation, right? I'm calculating the values of motor torque. Then if I look into that calculated values, then you can see that the highest value of torque the motor can develop is, in this case, it is 99, and it is when the slip is 0.14. Then with these calculations, I can say that whatever the motor you have designed with the rotor circuit parameters, R2 is equal to 0.12, X2 naught is equal to 0.85, like that. When it is excited with 240 volts and 50 hertz, will have a maximum torque of 99, and it is occurring when the operating slip is 0.14. Like this, I can tell, right? Is this point clear? Confirm me. Is this point clear? Confirm me. So basing on that, can I give the statement for the maximum torque? It is the highest value of torque. It is the peak value of torque the motor can develop for a given design parameters and for a given excitation parameters. So with that given design parameters and with that excitation parameter in the range 0 to 1, the highest value of torque the motor is developing is called as the peak value, or it is the maximum value, right? So I'll give the statement for this maximum torque. It is the highest value of torque. It is the highest value of torque, highest value of torque the motor can develop for a given design and excitation parameter. Excitation parameters. Given design and excitation parameters. Is this point clear? Confirm me. Is this point clear? Confirm me. Or I can define in other way also. Or what is that other way means? It is the torque after which the rotor is pulled out from stable to unstable state. See, in my definition, what is called as stable condition means the motor is able to supply the required load torque and it is rotating stably. It is rotating continuously. So if the motor is able to supply the required load torque, then the motor will continuously rotate. It will be rotating stably. But very unfortunately, if the motor is not able to supply the required load torque, then the motor will come to standstill position or stopping position. So that situation I call it as unstable. So whenever I'm using the condition stable here, so please remember, stable means the motor torque is equal to load torque. The motor is able to supply the required load torque. Then I'm calling that one as a stable condition. But very unfortunately, if the motor is not able to supply the required load torque, if it is failed to supply the load torque, then I can say it is unstable state, right? So last time also I told you, stable means the motor torque should be equal to the load torque. Unstable means the motor torque is not equal to the load torque. So here, if you are going on increasing the load, a situation will come that beyond that the motor will come to unstable state. What is the meaning of unstable state? The motor will say, I cannot supply the required load torque. The load torque is more than my capacity, more than my maximum value. I cannot supply the load torque. I'll slow down and finally I'll come to standstill position. So it was rotating stably. The TEM is equal to TL. But if you are loading the motor beyond this, the motor will come to standstill or it is unstable state. So this torque we call it as maximum torque, right? Confirm me all of you, right? So can I say it is the torque? It is the torque. It is the torque after which the motor is pulled out from stable to unstable state. Stable to unstable state. So I hope you understood what is the definition for maximum torque. Yesterday also I gave the definition for full load torque. So this is the definition for maximum torque, right? Now the question comes, how to calculate the maximum torque of a given motor? So you may have a misconcept that using this procedure we can calculate the maximum torque. What is this? Whatever the motor parameters are there, I'll substitute in the torque equation. Whatever that excitation parameters are there, I'll substitute in the torque equation, and I'll take different values of S ranging from 0 to 1, like 0.1 like that, and for that I calculate the magnitudes of torque. Then from that calculated, I'll pick up the highest one and I can say it is the maximum torque. So this we call it as a substitution method or direct calculation method. But very unfortunate thing is, what is the problem we are having with this method is, say this may not give the true value of maximum torque. The reason is, say if I would have calculated for 0.141, if I would have calculated, the answer would have been 99.89 or 9787 Newton meter. So I missed this value. So this approach, this substitution approach, this calculation approach may not give. See, Bhargav, I think there is no disturbance from my side. Maybe from your side, disturbance, right? Why? Because I can see. Okay, 1 second. Yeah, I can see. Right, I can see now. Okay. All of you has raised that. Okay, I'll come. 1 second. I'll come back. Now it is clear. Confirm all of you. It is clear. Confirm all of you. Right. Thank you, Baba. Bhargav. Right. So this we call it as a substitution method, or it is we call it as something like a direct substitution method or something like calculated method. So this method may not give the exact value of maximum torque. For that, we'll be having two approaches to calculate the maximum torque. What are those two approaches? Means one is the optimization techniques. The other one is maximum power transfer theorem approach, right? So here, this approach may not give the exact value. So I'll write a note here to find out the maximum, to find out the slip at maximum torque, and maximum torque value, we can use either optimization technique, second one is maximum power transfer theorem. So what is that optimization techniques? Let me explain first. Optimization technique, let me explain first. First, I'll explain what is called as optimization technique. After that, we'll come back to this maximum power transfer theorem. See, I'm having a function f of x. It is equal to x square plus 2x plus 2 or 1, 2x plus 1 or 2x plus 2, right? This is a function. So if I vary the value of x from minus infinity to plus infinity, if I vary the value of x from minus infinity to plus infinity, at a particular value of x, this function can exhibit either maximum value or minimum value. So if I want to know at what value of x this function will exhibit maximum or minimum, means I go for the single derivative, that is 2x plus 2 is equal to 0. So from this, x is equal to minus 1. So very compulsorily, this function at x is equal to minus 1 will have either maximum value or will have either minimum value. To know whether it is maximum or minimum, I'll go for the double derivative. Then you can see the double derivative is 2 here. 2 is greater than 0. Then at x is equal to minus 1, the function will be having a minimum value. So minimum value is nothing but the function value with x is equal to minus 1. If I do that, minus 1 square plus 2 into minus 1 plus 2, then the answer is 1. Then I can say this function will have a minimum value of 1 when x is equal to minus 1. Is it clear? Confirm me, all of you. Is it clear? Confirm me, all of you. Right. Now I'll consider the torque equation. What is the torque equation? 180 by 2 pi ns s E2 naught square into R2 by R2 square plus s x2 naught whole square. So what is the variable in this equation? You can see the variable is s. So if I want to get the condition for maximum torque, I have to differentiate that equation with respect to s, and I should equate to 0, right? So can I write to obtain the condition for maximum torque? Why? Because what is the variable there? Yes, to obtain the condition for maximum torque, differentiate this equation 1 with respect to s and equate to 0. I think this point is clear. Confirm me, all of you. Confirm. Right. But you can see only few what happened to others. Right. So please, then if you look into that equation, then you can see that s is present in both numerator as well as in denominator. Then if I want to find out the derivative, you have to go for u by v. So what is that u by v derivative? V derivative into u minus u derivative into v by v square should be equal to 0. If I do that, I'll get this condition. What is that? R2 should be equal to s x2 naught. So from this, I'll take out that slip and I'll write S is equal to Sm T max, or I can say Sm T. So what is that SMT means? It is R2 by X2 naught, and I name this SMT, that is slip at maximum torque. Slip at maximum torque. Slip at maximum torque. Slip at maximum torque. Then how to calculate the slip at maximum torque means using this relation R2 by X2 naught. Similarly, how to calculate the rotor speed at maximum torque? So that is equal to ns into 1 minus the slip corresponding to maximum torque. So it is ns into 1 minus R2 by X2 naught. So this I can call it a speed at maximum torque. That means when the motor is developing the maximum torque, what is the speed? Speed at maximum torque. Then how to calculate maximum torque? So you can see this is the general equation for torque for any value of slip ranging from 0 to 1. So from that you can calculate the maximum value. So if you want to calculate the maximum value in place of R2, you have to substitute Sx2 naught. When R2 is equal to Sx2 naught, the torque will be maximum. So can I say T max is nothing but the electromagnetic torque when R2 is equal to Sx2 naught. So that is equal to 180 by 2 pi ns S E2 naught square. In place of R2, I write S x2 naught by S x2 naught whole square plus S x2 naught whole square. In place of R2, I write S x2 naught whole square. If I simplify this, I'll get T max is equal to 180 by 2 pi ns E2 naught square by 2 x2 naught. So this is the equation for maximum torque. Is it clear? Confirm all of you. Is it clear? Right. So this is which approach of calculating the maximum torque means. This is the optimization techniques. What is that optimization techniques? So if I have a variable in any equation, and with respect to that variable, if I want to calculate the maximum value or minimum value, then first I need to differentiate that function with respect to that variable. Then I need to equate it to 0. Then I'll get the value of that variable at which the function will be maximum or minimum. Then to know at that particular value of variable, the function is maximum or minimum, you have to go for the double derivative. And if the double derivative is turned to be positive greater than 0, then you can have a minimum value. If it is less than 0, then you will be having a maximum value. So this you might have studied, and more or less in all the subjects you might have applied in transformers, in DC machines, in synchronous machines, you might have applied all these optimization techniques to obtain the maximum conditions. Is this clear? Confirm me. Confirm me, all of you. Right. See, one student wrote, take slip is equal to 1. See, Baba, if I take slip is equal to 1, so that will be the starting torque. Right? So if you take this S is equal to 1 here, so you can see in this, if I take S is equal to 1, so the value is 27.964. It is not the highest value. So when if you take S is equal to 1, you will not get maximum torque. Please remember that is the starting torque, right? Please. See, right. So just before I proceed, let me go for generally the maximum torque that a motor can supply is full load torque. No, sir. I told you that is the thing. The full load torque, it is not compulsorily to be a maximum torque. Just hold me for some time. I'll explain what is the difference. Right? Just I told you, just give me some time. Sir, can we call speed at maximum torque as the minimum speed? See, it is not a minimum speed beyond which the motor will come to standstill, or it is the minimum speed at which the motor will be rotating. After that, it will come to standstill, right? Good, right, right. Then what is that maximum power transfer conditions? So what is that maximum power transfer theorem means? If you recall, if I'm having a electrical circuit, I think you know, if I'm having an electric circuit, and if that electrical circuit is something like a Thevenin's model, what is the Thevenin's model? That means if I'm having a source and a resistance, it is called as a Thevenin's model. And if I'm having a load, then if maximum power has to be transferred from this source to load, then this load resistance should be equal to the source resistance. That is, RL should be equal to R. Then the maximum power will be transferred from source to load. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. So I'll apply the same thing here to find out the condition for maximum torque. Right. Next one is maximum power transfer theorem. Maximum power transfer theorem approach. Transfer theorem approach. So I'll take a rotor circuit. You or as of now, you can say motor circuit. What is that motor circuit you are having? It is R2 J X2 naught, and this is E2 naught. This is R2 by S. I'm sorry. So this is the equivalent circuit of the motor which you have designed as of now. Right? What is the condition for maximum torque? Right? See, if you recall the basic torque equation, it is 180 by 2 pi ns I2 square into R2 by S. This is the torque equation which we had derived already, right? So if I want to have this maximum torque, then you know that the torque depends upon the rotor input power. If the input to the rotor is maximum, the torque developed by the motor will be maximum, right? Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. All right. So which branch in the rotor circuit is consuming power means resistor. What is the value of that resistance? R2 by S. If this R2 by S is consuming maximum power, then the rotor input will be maximum. If the rotor input is maximum, the torque will be maximum. So can I say, if this rotor input is maximum, PRI is the rotor input is maximum, then this torque will be maximum. So for maximum torque, this R2 by S should consume maximum power. Should consume maximum power. If R2 by S is consuming maximum power, the rotor input is maximum, the torque which depends on that will be maximum. Is it clear? Confirm me. Confirm me. Right. Now what I will try to do means, I'll try to modify this circuit and try to shift this branch as a load branch. Why? Because you can see this torque is dependent on R2 by S. If R2 by S is consuming maximum power, the torque will be maximum. I'm modifying the rotor circuit according to the requirement. Modifying the rotor circuit. But when you are modifying the rotor circuit, the original things should not change, right? The current should not change according to the conditions. According to conditions. Right? So if I modify that, this is Jx2 naught, this is R2 by S, this is E2 naught, right? This is the modification. Then if I'm treating this one as a load impedance, then R2 by S should be equal to X2 naught. From this, From this, R2 is equal to S X2. So this is the equation for our condition for maximum torque. The same condition we got, the different condition. You can see we got the same condition. Is this point clear? Confirm me all of you. Confirm me all of you. Right. So like this, you can find out the condition for maximum torque either by using that optimization technique or by using this maximum power transfer theorem approach, right? Now let us see for this problem, which we have seen yesterday. For this problem, I told you it is a common data. For this problem, see, this is a motor which we have designed. This is a motor which we have designed. If the full load slip is 4%, what is the torque it is developing at 4% slip? 52.38. Now what I want to do is, the motor which we have designed, I want to calculate what is the slip for maximum torque and what is the value of maximum torque. I need to find out, right? Let us see. For the above problem, so that above problem is the common data. For the above problem, above problem, calculate 1. The slip at maximum torque, 2. The maximum torque. Do it. I'll give some 2 minutes time. Do it. Just 1 second. Do it. Meanwhile, give the answer. Do it. Right. What is the answer? So ST max is 0.141, T max is 99.86 Newton meter. Correct. Very good. Very good. Very good. Very good. What is the formula for ST max? ST max is R2 by X2 naught. It is 0.12 by 0.85. So it is 0.141. Then what is the value of T max? T max is equal to 180 by 2 pi 1000, right, into 76.98 whole square by 2 into 0.85. So this torque will be 99.86 Newton meter. So this is the maximum torque. Is this point clear? Confirm me all of you. Is it clear? Right, done. So this is something about your maximum torque. Now let us go for some observations. Very, very important concept, observations. Observations. See, Baba, when I'm trying to talk about observations, please remember these are the questions which are being asked in the previous competitive examination, right? Please try to understand these observations. 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 So what is that equation for maximum torque? T max is equal to 180 by 2 pi ns E2 naught square by 2x2 naught What is the equation for ST max? It is R2 by X2 naught. And what is the rotor speed at maximum torque? Already we have seen ns into 1 minus R2 by X2 naught. So this is something about your maximum torque values. The first thing is keeping all other parameters constant. If I vary the supply voltage, what happened to maximum torque? So we are varying only the supply voltage. So keeping other parameters constant. Then if that is the case, maximum torque is directly proportional to E2 naught square, directly proportional to E1 square, directly proportional to V square. I can say maximum torque is directly proportional to supply voltage square. Supply voltage square. So if the input voltage is reduced by 10%, then what happened to the maximum torque of that motor? The maximum torque of that motor reduces approximately by 20%, right? So this question was asked many times. If the input voltage is reduced by 10%, what happened to the maximum torque of that motor? Decreases approximately by 20%. So that is the reason I told you we are supposed to operate the motor always with that rated voltage, the nameplate details. Why? Because if we're trying to reduce that, the torque of that motor will reduce drastically, right? Please note this point. Is it clear? Confirm? Confirm. So can I say if the input voltage is reduced by 10%, T max reduces approximately by 20%. Approximately by 20%, right? Is it clear? Right. Second point is, if you see this torque equation, in this torque equation, we don't have any resistance parameter. So can I say by adding some additional resistance in the rotor circuit, we cannot change the maximum torque. But you know that by adding some resistance, we can improve the starting torque, right? So what is the maximum torque? So when the motor is already in the motion, the maximum torque can be, that is called as maximum torque, right? Right. Before to that, let me explain the difference between full load torque and maximum torque, right? The time has come, right? See, if you remember, after that, I'll come back that. What is the value of full load torque of this particular motor? 52.38 Newton meter. What is the maximum torque of this motor? 99.8 Newton meter. Now let me tell the difference between these two torques. The full load torque is the safest torque what the motor can develop without heating up of the windings, without damage of the windings. Already you know the full load torque is nothing but the torque developed by the motor with rated voltage and rated current. So this is the safest torque, or this is the torque designed by the manufacturer. Is this point clear? Is this point clear? Right. So what is that maximum torque means? It is the highest value of torque the motor can develop. Then what is the difference between these two, sir? There is a difference. See, if I'm trying to load the motor beyond full load, will the motor rotate? Yes, the motor will rotate. The motor will rotate. 1 second. The motor will rotate. So if I'm trying to load the motor beyond full load torque, will the motor rotate? Yes. Up to what level it will rotate? Up to maximum torque it will rotate. But if I'm trying to load the motor beyond maximum torque, will it rotate? No, it will come to standstill position. The motor will completely stop. So after which torque the motor will come to stopping position means maximum torque. So if you are going to load the motor beyond its maximum torque value, the motor will come to standstill position, stalling position, or stopping position. But if you are trying to load the motor beyond full load, beyond that rated value, will it rotate? Yes. But the problem is, if you are loading the motor beyond the full load torque, the windings will carry the currents more than rated value. When the windings are carrying the currents more than rated value, the temperatures will be very high. That insulation will start melting up, and that situation we call it as overload. Overload. So what is the meaning of overload? Means loading the motor beyond its rated value. We call it as overload. So in this overload condition, the motor can supply the load torque, but the windings will get heated up. And if you're trying to keep the load for long time, then definitely the windings will get damaged. So can I say a small example? You take a railway coolie. The safest weight what a railway coolie can carry is say some 100 kg weight. So without any difficulty, he is able to carry 100 kg weight. But if you're putting some 1-2 kg weight extra, then that fellow will say, "Arey, it is like burden to me. You are overloading me. Please try to remove. Please try to remove." So for some time, that heavy weights or extra weight he can carry for some time. But if you're keeping that weight for longer time, a stage will come that fellow will get collapse. So between the full load torque and maximum torque, that is the extra torque what the motor can supply for short time, very short time. But in this time, the windings will carry very high currents more than the rated value. And if you're keeping this load for longer time, the windings will get damaged. So that is the reason it is not advisable to load the motor up to maximum torque, but the safest value is only up to full load. But for short time, for a very short time, the motor can be loaded up to maximum. But if you're loading the motor beyond maximum, the motor will come to standstill position. I hope you understood the difference between full load torque and maximum torque. Full load torque is the safest torque. The motor can supply the load, but beyond full load torque, the motor can supply the torque, but it is only for short time. But if you're trying to load the motor beyond maximum torque, the motor cannot rotate, it will come to standstill position. So if you're loading the motor beyond full load torque, we call it as the overload condition. So that overload, the motor can hold only for some time, but if you're keeping that load for longer time, the windings will get damaged. I hope you understood the difference between full load torque and maximum torque. Clarify, confirm me all of you. Right. So generally, so the full load torque will be half of the maximum torque generally. Then we can say the design is good. But if the full load torque is like 1/4 of the maximum torque, the design is not good. So we generally design that the maximum torque will be almost double the full load torque. Double. That means the cushion torque will be around rated torque value. In this case, what is the full load torque we are having? 50 Newton meters. What is the maximum torque we are having? 100 Newton meters. Then you can see the full load torque is half of the maximum torque. That is a good design. But if you are designing the full load torque less than, say it is a full load torque is 20 Newton meter, maximum torque is something like 80. So you're wasting most of the torque. That means the cushion torque is more. So the proper design we cannot call. So for a proper design, the full load torque should be always or approximately equal to half the maximum torque, right? Is it clear? Confirm me all of you. Confirm me all of you. Right. So done. Now first observation is over. What is the first observation? Now I think most of the student got the clarity. What is the difference between, right? See, Mr. Sai Charan Reddy said, why the motor stop? Why? Because the reason is the active power drawn from the rotor will decrease. Already I told you yesterday, when you are increasing the load, I'm talking in depth. When you are increasing the load, a situation will come that this reactance part will be dominating that so-called as that resistance part. Then the active power drawn from the supply will start decreasing. When the active power drawn from the supply is decreasing, then the required torque to drive the load will start decreasing. A stage will come, this torque is not in a position to supply the torque, the motor will stop rotating. Sai Charan Reddy, is this point clear? Right, done. Right, done. So this is something about your maximum torque. First point, what is it maximum torque? First observation, maximum torque is directly proportional to square of the supply voltage. If the input voltage is reduced by 10%, the maximum torque value of that motor decreases approximately by 20%. The second point is, you can see in this, there is no resistance parameter. That means maximum torque is independent of the rotor winding resistance. Why? Because you know that by adding rotor winding resistance, we can improve the starting torque. Starting torque means torque during starting we can improve, but the maximum torque of that motor cannot be improved by adding some resistance. So this question was asked many times. Maximum torque depends upon the rotor winding resistance or independent? It is independent of the rotor winding resistance. But you can see the slip and the speed at which the maximum torque occurs depends upon the rotor winding resistance. And you know that in case of slip ring induction motor, we have the provision of adding resistance. And by adding resistance, we cannot change this maximum torque value, but we can get the same maximum torque at any slip or at any speed, right? Second point is maximum torque is independent of rotor winding resistance, but the slip and the speed at which maximum torque occurs depends on R2, right? In case of slip ring induction motors, by adding external resistance, Tmax can't be changed, but the slip and the speed at which Tmax occurs can be changed. Is this point clear? Confirm me. Is this point clear? Confirm me. All right. One question is, sir, can we get the maximum torque at any desire? Yes, you can get the maximum torque even at starting also. We can get. There is no issue at all. Sir, if we improve the insulation, then we can use motor up to maximum torque. Obviously, yes. But unfortunately, if you are increasing the insulation, the size of the stator slots will increase. When the size of the stator slots increases, the size of the machine will increase. Like overall size of the machine increases and cost will go, right? So it is only the cushion torque. So we can increase, everything we can increase. But if you are increasing the size of the insulation, what happens? Everything will increase. So we cannot do that. So it is something like this. So the additional load, what the motor can supply for short time, that we call it as maximum torque. So that additional load cannot be for all the times. It is only for short time. Then the motor has to supply. It is a cushion period, cushion torque, which the motor can supply for short time. Gokul Sham, is it clear? Right, done. Right. Please explain second point. See, you can see the nothing there in the second point. So maximum torque is not having any resistance. By adding resistance, we cannot change the maximum torque value. So maximum torque is independent of resistance, but the slip and the speed at which the maximum torque occur depends upon resistance. So in case of slip ring, you know, there is a provision of adding resistance. By adding that, we can vary the slip and the speed, but not the value of maximum torque. Is this point clear? Confirm me, all of you. Raise the hands. Raise the hands. Right, done. Third point and very, very important point is C. Third point and very, see if I am correct, roughly some 10 hours I spent on the construction. Now you can see the importance of construction now. You can see why we have spent so much time on construction. You can see now. Why? Because whatever I discussed now, they are like related to your construction part. Let us see what is it. See. Fine. So Tmax, if I keep all other parameters, is inversely proportional to leakage reactance. At standstill, right? See, sir, by adding resistance, we can control maximum torque. अरे बाबा वही बताया था ना प्रतीक प्रमोद. So we cannot control maximum torque. So the maximum torque of a motor doesn't depend upon resistance. So we cannot control. Once the motor design is over, the maximum torque of that motor is fixed. We cannot change that. Pramod, right? So you can see maximum torque is inversely proportional to leakage reactance. So from this I can say, if the leakages are more, the maximum torque is less. If the leakages are less, the maximum torque will be more. Very simple relation, very simple. If the leakages are more, then obviously the power transfer to the rotor will be less. Why? Because if the leakages are more, then obviously the motor circuit will be high inductive in nature, then active power drawn will be less and the torque which depends on that will be less. So that is the reason always you need to design any induction motor with very less leakage reactance at startings, right? So if this leakage reactance is less, obviously the maximum torque of that motor will be very high. So maximum torque is inversely proportional to leakage reactance. More the leakages, lesser the starting torque, lesser the leakages, more the maximum torque. Is this point clear? Confirm me. Confirm me. Right. So what I'll do means I'll consider two motors now. Motor A, motor B. See, whenever I'm comparing two motors, please remember they are identical with respect to construction wise, everything they are identical. But the thing is, one is a squirrel gauge induction motor, the other one is a slip ring induction motor. Only the difference is the motors. One is a cage rotor, the other one is slip ring motor. Now I want to compare the maximum torque of these two motors. So even though their constructions are same, only the rotor circuit difference is there. Then in which case the maximum torque will be more, in squirrel gauge or in slip ring, right? The answer is, in case of squirrel gauge, the maximum torque will be slightly more than the maximum torque of a slip ring. The reason is, if you recall, in case of squirrel gauge, the rotor doesn't carry any windings. When there are no windings, there are no turns. There are no turns. But whereas in case of your slip ring, the rotor carries windings, so we are having turns. When we are having turns, the leakages in that rotor circuit will be more, the leakage reactance will be more, and comparatively the maximum torque of that motor will be less. So if I'm having a squirrel gauge induction motor and slip ring induction motor, they are identical. Everything 5 HP, 5 HP, frame size is same, air gap same, everything is same. But I want to compare in which motor the maximum torque is more. Means you can say the maximum torque of a cage rotor is slightly more than the maximum torque of a wound rotor. Why? Because a squirrel gauge rotor doesn't carry any windings, so the leakage reactance will be less. When the leakage reactance is less, obviously the power coming to the rotor will be more, and obviously the maximum torque of that motor will be high. So which motor will be having comparatively more maximum torque means a cage rotor. Is this point clear? Confirm me. Is this clear? Right. So the question will be asked like this, and many times it was asked, what is it? I'm having two induction motors, A and B, which are identical, but one is a cage motor, the other one is a wound rotor. So which motor will have comparatively more maximum torque if all other parameters are kept constant? The answer is cage rotor. Why? Because the leakages, there are no winding, the leakages are less, and the maximum torque of that motor will be slightly more, slightly more. So here I can say this squirrel gauge will have more maximum torque. Is this point clear? Confirm me. Confirm me. Right. Fourth point, very important point. Now I'm having a cage induction motor, squirrel gauge induction motor only, but one is using open slots, one motor is using open slots, one motor is using semi-open slots, and one motor is using closed slots. Motor is same, cage rotor only, but one uses open slots, semi-closed slots, and closed slots, in which case the maximum torque will be more. If you remember, the leakage reactance with open slots is less. Don't ask now. I have spent maximum time on this. Compared to semi-open, compared to closed. So in which case the leakages will be more, means in closed slots, the leakage will be more. This was already explained to you. Don't ask now, right? You refer the notes. In closed slots, the leakages will be more. If that is the case, in which case the maximum torque will be more, means the maximum torque with open slots will be slightly more than the maximum torque with semi-open, slightly more than the maximum torque with closed slot. I think this point is clear. Confirm me all of you. Confirm me all of you. Right. Very good. Very good. Right. So please recall all those constructional points here. Right. Please. And the next and important point is here. So how the question will be framed in this means in point 4, how the question will be framed means there are two squirrel cage induction motors which are identical. One uses open slots, the other uses closed slots. So comparatively, which motor will be having more maximum torque? The open slots, right? The next point is I have a squirrel cage induction motor and I am using open slots only. Open slots only. But one is narrow slot. The other one is wider slots. In which case the leakages will be more, means C. If you try to draw this, this is the stator circuit. These are narrow slots. Narrow means the slots are made deeper into the core, rotor core. Wider means this one is the stator. This is the wider. The slots are not made deeper, but the width is more. You can see the slots are made only on the outer surface, very closer to air gap. I hope you understood the difference between narrow and wider. Confirm me all of you. Right. And if you go inside the core, when you are going inside the core, the permeability of the core will increase and the magnetic flux lines will be completing their path inside. The leakages will be more. I think you know by definition what are called as leakage flux lines. Leakage flux lines are those which are completing their path linking with only one circuit. So rotor circuit here. But here you can see these are the leakages. So in which slots the leakages are more means you can see in narrow slots the leakages are more. When the leakages are more in the narrow slots, the leakage reactance is more and the leakage reactance is less here. When the leakages are more in the narrow slots, then the leakage reactance more means the power which is coming to the rotor will be less. If the power which is coming to the rotor is less, the torque which depends on that will be less. So in which motor the maximum torque will be more in squirrel cage in open slots compared to narrow and wider means in case of wider the maximum torque will be more. Why? Because the leakages will be less. Why? Because when you go into the core, as the permeability is more, those flux lines will be completing inside. But when you are closer to the air gap, so those flux lines will be completing between stator and rotor. So less flux lines will be completed within the rotor here. So in which case the leakages will be more here. The leakages are more in narrow slots. Is it clear? Confirm me. Confirm me. So can I say like this? So the maximum torque here is less. The maximum torque is less. The maximum torque is more here. So can I write finally? So the maximum torque with narrow slots is slightly more than the maximum torque, less than here. Wider slots. Is this point clear? Confirm me. Is this point clear? Confirm me all of you. Raise the hands. Right. Which sixth point? The last point here is C. Sixth point, the last point. Now I want to explain on the basis of air gap. Air gap. So you know that in case of a cage rotor, the air gap is small. Squirrel cage induction motor, the air gap is small. smaller air gap. Why the air gap is small means as the rotor doesn't carry any winding, the rotor surface is very smooth. When the rotor surface is very smooth, we can leave a smaller air gap, right? Done. But when I'm talking about a slip ring induction motor, due to the windings on the core, you know the windings will be there in case of slip ring. Due to the windings, comparatively the air gap will be more. So in case of slip ring induction motor, this air gap will be comparatively more, is slightly more. When the air gap is slightly more, what happened to leakages? Already we have seen with the increase in the air gap, the leakages will increase. When the leakages increases, obviously what happened to the maximum torque decreases. So here, again on the basis of air gap, in which case the maximum torque will be more, means in case of squirrel cage induction motor, the maximum torque will be more. Why? Because the air gap is less, the leakages are less, the power transfer to the rotor is more, and hence the maximum torque will be more, right? So these are some observations. Let me repeat once. What is that? First one is the maximum torque is directly proportional to the square of supply voltage. If you are decreasing the supply voltage by 10%, then compared to the rated voltage, the maximum torque of that motor will be reduces approximately by 20%. The second point is the maximum torque doesn't depend upon the rotor winding resistance. Unlike your starting torque, we cannot improve the starting torque by adding resistance. So the maximum torque cannot be improved by adding some resistance here. But we can get that maximum torque by adding some resistance by varying that slip and by speed. So that maximum torque can be obtained at any slip or at any speed. So the remaining things are clear, right? Is it clear? All of you confirm me? Confirm me. I want to see all should raise the hands. Nearly 300 plus are there. Only I can see 67 are raising. How come, how leakage reactance come into account in the torque equation? You go through the torque derivation, already have derived the torque derivation. You can see how the torque reactance has come in the torque equation. This was already derived, Baba. Anonymous attend, you can go through that. The next concept is, see, I'm having an induction motor. When I'm giving a voltage V at a frequency F, then the maximum torque of this motor is Tmax, and the maximum that slip at maximum torque is SMT. Now for the same motor, if I'm decreasing the voltage to V by 2 and if I'm decreasing the frequency to F by 2, then what happened to this Tmax value and what happened to that STmax value? Now we are going to see the effect of variable voltage and variable frequency, effect of variable voltage and variable frequency on Tmax and STmax, right? Right. So on the what is the fifth point? Fifth point is we can see if the slots are narrow, it doesn't mean as you are going inside the core, the flux lines will be completing their path inside. Why? Because the permeability will be more. But if this you can see, if they want to complete this path, so they need to travel this much in air. But if they want to complete the path, they need to travel only this much in air. So in which case the permeability, in which case the leakages will be more means in this case. Please try to refer my notes, please, all of you. Right. So next concept is the effect of variable voltage and variable frequency on maximum torque. Okay. Once again, sixth point. See if the increase in the air gap. See, if the air gap is increased, what happened to leakages? See, Baba, this is not, I'm repeating, I'm telling for the first time. That is the reason I broke my head to remember the construction point. When you are increasing the air gap, what happened to the leakages of that circuit increases. When the leakages have increased, what happened to the power transfer to the rotor circuit decreases. When power transfer to the rotor circuit decreases, obviously what happened to the maximum torque of that motor decreases. It is a simple thing. Why you are asking to repeat that question 6, right? Please. Fine. So anyhow, I'll show these notes. I'll give these notes. Don't worry. The next point is effect of variable voltage, effect of, so if anyone want to take the notes, you can take this. Right. See, some students are asking personally to share the notes. Immediately I'm sharing the notes, right? Anyhow, the manager will keep it in the site. You can collect or you can download from that, right? From my side, immediately after the class, those who are asking, I'm sharing to them. Right, done. Now, next one is effect of variable voltage and variable frequency on Tmax and the slip at maximum, right? Let us see the effect, please. See, if I consider the maximum torque value, it is 180 by 2 pi ns E2 naught square by 2x2 naught, right? This is already derived. And if you go for the equations, in this ns, you are having 120 into f by p. There is one f. And in this x2 naught, 2 pi f into L2, there is one f. In the denominators, if I keep all other parameters, there are two f's. And this is directly proportional to numerator. E2 naught is directly proportional to E1, and it is directly proportional to the magnitude of the supply voltage. So if I mix up all these things, you can see maximum torque is directly proportional to the supply voltage magnitude square, and it is inversely proportional to the frequency of that supply voltage. So if I'm going to mix up all this, so Tmax is directly proportional to V1 by F whole square. Let me call that V1 as the supply voltage V. Then I can say Tmax is directly proportional to V by F whole square. This is one point to be noted. Is it clear? Confirm me. Is it clear? Confirm me. Right. This is one equation. Then what about that ST max? ST max. So ST max is equal to R2 by X2 naught. And in this X2 naught, there is one F. So from this, ST max is proportional to F. This is the equation, right? These are the two equations. Is it clear? Confirm all of you. Go through this. Go through this. This is one equation. Right? This is one equation, torque equation. Now the question is, see, I'm having a three-phase induction motor. Initially, the three-phase induction motor is excited with V voltage magnitude at a frequency of F. The developed maximum torque is T and the slip is S. Now what I'm trying to do means I'm trying to decrease the voltage to V by 2 and I'm trying to decrease the supply frequency to F by 2. Then when I'm decreasing that voltage to V by 2 and the supply frequency to F by 2, then what happened to that maximum torque of that motor and what happened to the slip of that motor at which the maximum torque occurs? Will they remain same or they are going to change? We are going to see that, right? Done. See how F square has come. See, this is 180 by 2 pi ns to x2 naught. In ns, there is one F, 120 into F by P, there is one F. In x2 naught, there is one F. If I keep all other parameters constant, F into F will be F square. So inversely proportional to F square. Pranay. Is it clear? Right. So we'll see these doubts. Done. Now let us go. What is that? I'm trying to vary the supply voltage magnitude. I'm trying to vary the frequency. See, before I proceed, one question I'll answer. See, when I'm clear with my discussion, I don't know why this Gokul Sham is having a doubt. See, Baba, please. Sir, but X2 naught is a standstill reactance, which is a constant. I agree that X2 naught is a constant value. But when I'm talking about a squirrel gauge induction motor and slip ring induction motor, in case of squirrel gauge induction motor, whatever you are calling it as a constant, X2 naught is less, and whatever that X2 naught in case of slip ring induction motor will be more. So comparatively, in which motor that X2 naught will be more, means in case of slip ring induction motor, that X2 naught will be more. When it is more, the maximum torque will be less. That is what I told. I never told that X2 is running condition and other things. Sham, you understood now? Gokul Sham. Samjha Baba? Is it clear? Raise the hands. So in which motor that X2 naught will be clear? Right, done. Gokul Sham. Right. Right. So we are not talking about frequency or anything. I told X2 naught. So in which motor that X2 naught will be more means in case of squirrel gauge, the X2 naught will be less. That's what I told. Right. Other things we'll see later. Right. Please. Fine. So let us go for that observations. Right. What I'm trying to do means I'm trying to vary. I'm not going to look into those question and answers now, please. So now I'm trying to vary the voltage magnitude and I'm trying to vary the frequency magnitude, but I'm trying to keep that V by F ratio constant. So keeping V by F ratio constant. Keeping V by F ratio constant. What is the meaning of that? Please see. Please see. Initially, I'm applying a voltage of V when the frequency is F. Let V by F ratio is V by F only. Now I'm reducing the voltage to V by 2 and frequency also to F by 2. Then what is that V by F ratio here? It is same. So V by F ratio is same. Then in the first case, if T max 1 is equal to T and ST max or SMT is 1 is equal to S. Then in the second case, what happened to the value of T max 2 and what happened to this ST max 2? What are the values? So here you are keeping that which ratio constant here, V by F ratio are keeping constant, right? So here you can see as V by F ratio is constant, what happened to the maximum torque? So if you recall, E1 is equal to the supply voltage V, if I neglect the drops, 4.44 F phi R N1 KW1. So in this 4.44 is constant, N1 KW1 is constant. Then I can say E1 is equal to V1 is directly proportional to F into phi r. So from this, phi r is directly proportional to E by F or V by F. As V by F ratio we are keeping constant, then flux in the air gap will remain constant. So remember, whenever you are keeping that V by F ratio constant, the flux in the air gap will remain constant. Then you know that T max is directly proportional to V by F whole square, directly proportional to phi r square. Phi r square is constant here, so T max will remain constant here. So here, which one will remain constant means the magnitude of T max will remain constant. Is it clear? And S T max is inversely proportional to frequency. Now, what is the answer? So I'll take some numerical values. Please see. Initially, this voltage is something like 400. This frequency is 50 hertz. Frequency is 50 hertz. What is that V by F ratio? 400 by 50 is 8. Now I'm decreasing this voltage to 200 and I'm decreasing this frequency to 25 hertz. Again, what is that V by F ratio? 8. That means we are changing both voltage as well as frequency, and the change is proportionately we are changing so that V by F ratio is kept constant. If that is the case, what will be the values of T max 2 and ST max, SMT 2? So if I say with rated voltage and rated conditions, the values of T and S, then what is the value of this second one? The torque will remain same, but the slip is inversely proportional to frequency. As you are decreasing the frequency to half, then this becomes 2S. That means whenever you are changing the voltage and frequency, keeping that V by F ratio constant, there will not be any change in the maximum torque value. The maximum torque value will remain unchanged, but only the slip will change. As you are decreasing the frequency to half, then the same torque will obtain when the slip value is 2S compared to that ES. Is this point clear? Is this point clear? Confirm me. Right. The question will be something like this. What is that question? Please go through this question. What is that question means? By keeping V by F ratio of an induction motor constant, so whenever the terminology V by F ratio is kept constant means indirectly he mean to tell to you that both voltage and frequency are varied and they are proportionately varied, V by F ratio is kept constant. So by keeping V by F ratio of an induction motor keeping constant, if the supply frequency is reduced to half, if the supply frequency is reduced to half, then what happened to the values of maximum torque and what happened to the value of slip at maximum torque? The answer is there is no change in the maximum torque value, but the slip will be doubled. The slip will be doubled. The maximum torque value will remain same. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. The next point is in this case, this is case 2. The first one is case 1. I'm keeping voltage constant, but I'm changing frequency alone. So we are changing frequency alone. So half or anything, we are changing frequency alone. So in this case, V by F ratio will not be kept constant. Is not at all constant. Why? Because you are changing only which parameter? Frequency. As V by F ratio is not kept constant, then your phi r will not remain constant. Phi r will not remain constant. If that is the case, T max is directly proportional to V square and inversely proportional to F square. Here you can see as we are not changing the voltage, this voltage will remain constant. Then this T max is inversely proportional to F square and St max is inversely proportional to F. Inversely proportional to F. So the question will be something like this. The question will be something like this. What is that? Keeping the supply voltage of a three-phase induction motor constant. Keeping the supply voltage of a three-phase induction motor constant. If the supply frequency is reduced to half, if the supply frequency is reduced to half, then what happened to the maximum torque value? What happened to the slip at maximum torque, right? So the answer is, so here V2 I'm not changing, V2 is same, but I'm changing the frequency to F by 2. So here V by F ratio is not constant. Then if that is the case, maximum torque is inversely proportional to frequency. As frequency is reduced to half, then this T max 2 becomes 40 and this slip at maximum torque becomes 2s. I hope this is clear. Confirm me all of you. Confirm me all of you. Right. Only few. What happened to others? All raise a hands. Right. The last point. Hope you can tell what is the last point. Case 3. What is that last point? I am varying the magnitude of voltage. Frequency is kept constant. V by F ratio is not kept constant. Then phi R is not constant. Then T max is inversely directly proportional to V square and inversely proportional to F square. Here F is constant. So T max is directly proportional to V square and St max is B constant. So what is the example? I'll be taking V2 is equal to V by 2 and F2 is same as F. V by F ratio is not constant. Then T max 2 is equal to T by 4 and S max 2 is equal to S. So this is something about your fourth point. Is this point clear? Confirm. Is this point clear? Confirm, all of you. Right. So if anyone want to ask any question from this maximum torque concept, so we have seen everything. So no concept is left uncovered, right? So that you can miss any question from your maximum torque. Once again, I repeat, what is this maximum torque? Maximum torque is nothing but the highest value of torque the motor can develop for a given design and excitation parameters. Or it is the torque after which the motor is pulled out from stable to unstable state, right? This is the definition for maximum torque. Now the question comes, how to find out the maximum torque value of a given motor, the slip at which the maximum torque will occur. So we have two approaches. We are having two ways. One is the optimization techniques. The other one is the maximum power transfer theorem approach. In optimization technique approach, whatever the torque equation we have, in that the variable is S, we have to differentiate the torque equation with respect to S and you should equate it to 0. Then we got the condition like R2 is equal to S, X2 naught. From that we got what is the slip, how to find out the slip at maximum torque. Then we calculated the maximum torque equation. Is this point clear? Confirm me. Confirm me. Then after that we have seen some observations. What are those observations? So with respect to the design parameters, how this maximum torque value will change. One is, if you are varying the supply voltage magnitude, keeping all other parameter constant, the maximum torque is directly proportional to the square of the supply voltage. Second one is, you can see the maximum torque is not dependent on the rotor winding resistance. So from this, it is very much clear that the maximum torque value cannot be altered cannot be varied by adding an additional resistance in case of rotor circuit of a slip ring. But the good thing is we can get the same maximum torque at any value of slip or at any value of speed. That maximum torque can be obtained even at starting also. Next one is maximum torque is inversely proportional to the rotor standstill leakage reactance. The motor with more leakage reactance at starting will have less maximum torque compared to the motor leakage reactance or less leakage reactance at starting. So if I'm having a squirrel cage induction motor, a squirrel cage induction motor doesn't have windings and hence the leakage reactance will be less and comparatively the maximum torque will be more, right? Just 1 second, let me screen this. Right. So like this, you have seen the other points with respect to maximum torque. Is this clear? All of you confirm me? Confirm me? Right. The next performance parameter is the starting torque, right? Starting torque. Starting torque. So what is that starting torque means? The torque developed by the motor at starting when you are applying rated voltage, right? So with rated voltage, whatever the motor torque at starting, we call it as a starting torque, right? Starting torque. Starting torque. And we represent the starting torque with T suffix ST. See, in some textbook, they use some other notation, T suffix S. I'm using T suffix EST, no problem. So what is the definition for starting torque? It is the torque developed. See, whenever I'm talking about the torque, it is an electromagnetic torque only. Please remember, it is the torque developed by the motor at starting. Starting means what is the value of NR? NR is equal to 0. What is the value of slip? 1. Starting NR is equal to 0, S is equal to 1 with a rated voltage. With rated voltage, right? And rated frequency. So can I say starting torque is nothing but one value of electromagnetic torque with S is equal to 1. S is equal to 1. So I'll substitute that S is equal to 1 in that torque equation. 180 by 2 pi ns. In place of that S, I'm writing 1 E2 naught square into R2 by R2 square plus 1 into x2 naught whole square. So whatever the torque equation we have in that, what is the torque equation? I'll show. Again, we'll have. See, in this torque equation, in place of S, I'm writing 1. Then that is nothing but the equation for your starting torque. So what is the equation for starting torque? T start is equal to 180 by 2 pi ns E2 naught square into R2 by R2 square plus x2 naught square. So this is the equation for starting torque. Is this point clear? Confirm me, all of you. Confirm me. Right. Get ready with the calculators. For the above problem, the common data problem, which we have seen yesterday. For the above problem, for the above problem, for the above problem, calculate starting torque. Do it. I'll wait for time. Do it. I'm waiting. Please do it. See, no one has given the answer. 27.64, 27.64. Very good. So answer is 27.64. So answer is 27.64. T start is equal to 180 by 2 pi into 1000 into 76.98 whole square into 0.12 by 0.12 square plus 0.85 square. If I simplify, 27.64 Newton meter. So this is something about your starting torque, how to calculate starting torque, right? So let me update. Arey Baba, see, one thing I told you yesterday. First, we should learn what is that we are learning. Then after that, you learn that. If anyone questions you, or what is that you are learning now? See, our intention is to find out the performance parameters of a three-phase induction motor if I know the rotor circuit parameters. What are those rotor circuit parameters? R2, X2 naught, and E2 naught. These are the only rotor circuit parameters. In any problem, R2 will be given directly, X2 naught will be given directly. The only parameter which will be given indirectly is E2 naught. So what are those three possibilities that E2 naught may be given? First possibility is that E2 naught may be given directly. That E2 naught may be given like the voltage across any two slip rings may be given at starting. From that you can calculate E2 naught. Third one is the supply voltage may be given. From that you can calculate E2 naught if the turns ratio is given. These are the three. Now, if you know this R2, X2 naught, E2 naught, is it possible to calculate the complete rotor circuit parameters or the motor parameters? Yes. What are the things we can find out? I can find out the rotor input power. What is the equation for the rotor input power? It is 3I2 square into R2 by S. Now you want to find out at what value of S. Then first you have to calculate I2. I2 is equal to E2 naught by square root of R2 by S whole square plus X2 naught whole square. From that you can calculate I2. Like that we can find out rotor input, rotor losses, rotor output we can find out. Is it clear? Confirm me. Confirm me. In addition to that, I can calculate the full load torque of the motor if the full load slip is given to me. I can calculate the maximum torque of that motor by because I can calculate slip using formula R2 by X2 naught. I can calculate the maximum torque and I can calculate the starting torque of that motor. So this is what I can find out as of now if only the rotor circuit parameters are given. So please keep this in mind. R2, X2 naught will be given, E2 naught may be given in different ways. From that you have to grasp that and you have to calculate, you can calculate all these things, right? So now we have calculated which torque of that motor, the starting torque of that motor, right? Now let us see some observations with respect to starting torque. After this, I'll give the break, right? Please, is it okay? Please confirm me. Right, observations. See, one has to know what is it you are learning, then only you can learn. Observations. Observations. What is the equation for starting torque? We have seen starting torque is equal to 180 by 2 pi ns E2 naught square into R2 by R2 square plus X2 naught square, right, please. So if I keep all other parameters constant, starting torque is directly proportional to E2 naught square, directly proportional to E1 square, directly proportional to V1 square. So from this, I can say starting torque is directly proportional to supply voltage square, supply voltage square. So this equation says that if the input voltage is reduced by 10%, then the starting torque of that motor decreases approximately by 20%, right? So can I say if the input voltage is reduced by 10%, T starts reduces approximately by 20%. 20%. Is this point clear? Confirm point clear? Confirm all of you. Right. The second point and very important point, for any induction motor, the value of R2 will be ranging from 1 ohm to 0.2 ohms for induction motor. And X2 naught is 1.5 ohms to 2 ohms generally. So if I consider any lower extremities or upper extremities, R2 I take it as 0.1 ohm, then what is the value of R2 square? It is 0.01. If I take X2 naught as 1.5 ohms, then X2 naught square will be 2.25. Then you can see when compared to R2 square, that X2 naught square is very large. 2.25 is very large. So can I say R2 square is much lesser compared to your X2 naught square? Then in the starting torque, which parameter I can eliminate or remove, means I can remove R2 square. See, compared to R2 square, X2 naught square value is very less. So that means calculating starting torque with R2 square or without R2 square, the answer will be more or less same. That is the reason compared to X2 naught square, we are ignoring R2 square. If that is the case, starting torque is equal to 180 by 2 pi ns E2 naught square to R2 by X2 naught square. If I keep all other parameter constant, then I can say starting torque is directly proportional to R2, right? It is the rotor winding resistance. So this equation I told you to remember during my starting classes. Basing on this, I told you that the starting torque of that induction motor is very less. But truly speaking, what is the reason? The rotor circuit is highly inductive. That is the reason the starting torque is less. So from this equation, can I say like this? By adding some resistance in the rotor circuit at starting, then we can improve the starting torque. But it is possible only in which motor? It is only in case of slip ring induction motor. Is this point clear? Confirming. But when you are adding resistance, what is that you are doing? When you are adding resistance, you can see when compared to this reactance part, you are making the rotor circuit highly resistive. So when you are making the rotor circuit highly resistive during starting, then obviously the active power drawn from the source at starting will be more. Why? Because the power factor will be approximately unity. When that active power drawn from the source is more, then obviously the torque which depends on that will be more. I think this point was already been explained to you in the previous classes. Confirm me, all of you. Confirm me. Right. So can I say starting torque is directly proportional to see, one thing I want to remind you, whatever the stuff I'm giving, you search any textbook. maybe your PS Kimra, Nagratan Kotari, electrical machines by Chapman, whatever the textbook, no, this much stuff will be given. Why? Because I feel strongly that being an electrical engineer, you are not supposed to learn anything on the basis of equations. Equations are used only to find out the magnitudes of that particular parameter, starting torque, like that. So here, this is only for your satisfaction. Starting torque is directly proportional to resistance. But I told you at starting, as the rotor frequencies are equal to the supply frequencies, compared to your R2, that X2 naught is very high, larger value, rotor circuit will be high inductive in nature. The power factors will be very less, the starting torque will be very less. But in case of your slip ring induction motor, if you're adding some resistance in the rotor circuit, so compared to that reactance X2 naught, you're making the circuit high resistive. When you're making the circuit highly resistive, then the power factor will be more, and obviously the starting torque will be more. Is this point clear? Confirm me. Confirm me. Right. So starting torque is directly proportional to R2. In case of slip ring induction motor, by adding R external, additional resistance in the rotor circuit, T start is increase. T start is increase. I hope this point is clear. Confirm me all of you once. Confirm me all of you once. Right. Third point. You can see here starting torque, see Baba, is inversely proportional to square of the rotor leakage reactance. I'm talking with respect to leakage reactance at starting. So which motor will be having more leakage reactance? X2 naught means a slip ring induction motor. Why? Because the rotor have windings, right? So most of the student will do a wrong analysis here. What is that? Slip ring induction motor doesn't mean that the starting torque is high. Wrong. Now what I'm trying to do is I'm going to compare the starting torque without external resistance. I'm not adding any external resistance. So external resistance is 0, sorry. External resistance is 0. Now I'm going to compare the starting torque. So starting torque is inversely proportional to square of leakage reactance. So in which motor the leakage reactance will be high, means slip ring. Why? The rotor have windings. So again, in which motor the starting torque will be less, means in slip ring only. So when we can improve the starting torque of that slip ring induction motor, means only after adding resistance. So tomorrow if anyone questions you like this in interviews or wherever it may be, or I am having two induction motors A and B. A is a squirrel cage induction motor, B is a slip ring induction motor. So can you please tell me in which motor the starting torque is more? Then you are not supposed to be hurry. Then you have to question him back. Sir, whatever the slip ring induction motor you are talking about, you have added any resistance externally in the rotor circuit? You have not added. No resistance added. Then in that case, the starting torque of a cage motor will be more compared to the slip ring. Why? Because in cage motor, as the rotor doesn't carry any winding, the leakages will be less and the starting torque will be more. If the question is, I have added some resistance, means in which case that starting torque will be more, means in case of slip ring. Is this point clear? Confirm. Is this point clear? Confirm. So can I say like this? I'm having an induction motor A and induction motor B. This is a squirrel cage induction motor. This is a slip ring induction motor with no added resistance. Added resistance is 0 here. So in which case the starting torque will be more, means only in case of cage rotor. Why? Because X2 naught in case of cage rotor is less. Fourth point is again the same story. I'm using a squirrel cage induction motor only, right? But I want to compare the starting torque on the basis of slots. So first one I'm using a open slots. Second one I'm using a semi-open slots. Third one I'm using a closed slots. In which case the starting torque will be more, means the starting torque in open slots will be more compared to semi-close compared to close. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Done. Fifth point is again, I'm using a squirrel cage induction motor only. Again, open slots only, but one is a narrow slot, the other one is a wider slots. In which case the leakages will be more. So it is narrow, more you go inside, more will be the leakages. When the leakages are more here, then the starting torque will be less here. Same story what we have discussed with respect to maximum torque. So in which slots the starting torque will be more, means the starting torque with narrow slots is less compared to the starting torque with wider slots. Is this point clear? Confirm me all of you. Right. Next and last point with respect to starting torque is again with respect to gap. A squirrel cage induction motor will be having smaller air gap in case of squirrel gauge. If the air gap is less, leakages are less. Say I'm not just giving a blind statement. Starting classes we have seen. And if I'm taking a slip ring, compared to the air gap will be more, slightly larger air gap. Right? So in which case the starting torque will be more, means in case of squirrel gauge. When I'm not adding any additional resistance, please keep this in mind. 0. So can I finally say like this? In case of slip ring induction motor, the starting torque can be increased. The starting torque can be improved only after adding external resistance, only by making that rotor circuit highly resistive compared to your leakage reactor, the value should be more. So when you are making the circuit resistive compared to your inductive nature, then only the starting torque can be improved. But when you are not adding additional resistance, then the rotor circuit will be high inductive. Even in case of slip ring, the starting torque will be less. I hope this point is clear. Confirm me all of you. Right. So before we go to the further topic, once again, let me repeat. So what is the starting torque? Starting torque is nothing but the torque developed by the motor at starting with rated voltage at rated frequency. Then how to derive the equation for the starting torque? We have the general equation for electromagnetic torque. And in that, if you take S is equal to 1, so whatever the torque the motor develops at S is equal to 1 is nothing but your starting torque. Then we have seen whatever the motor we have calculated, the starting torque value of that motor is 27.64. After that, we have seen some observations. What is the observation? Simple observation. The first observation is the starting torque is directly proportional to the square of the supply voltage. If you are decreasing the supply voltage by 10%, the starting torque decreases approximately by 20%. Similarly, the starting torque is directly proportional to rotor winding resistance. And if you are adding some resistance in the rotor circuit at starting, and if you are making the rotor circuit high resistive, then the power factors will be more, active power will be more, the torque developed by the motor will be more, starting torque will be increased. So you can see the starting torque is inversely proportional to the square of the rotor leakage reactance at standstill. If you are having a cage rotor, then the leakage reactance at starting will be less. Why? Because the rotor doesn't carry any winding. And there, in case of slip ring compared to this, the leakage reactance will be more and hence the starting torque will be less if you are not adding any additional resistance. Like that we have seen some cases. And finally, one very important point, after that we can go for a break. What does that means? If you remember, maximum torque is inversely proportional to leakage reactance starting torque is inversely proportional to square of leakage reactance. When we are increasing the air gap length is increased, then obviously the maximum torque will decrease and starting torque will also decreases. But which reduction will be more means the starting torque reduction will be more. Why? With the increase in air gap, the leakages will increase. When leakages increases, maximum torque decreases. But when the leakages increases, the starting torque double decreases. So can I say with the increase in the air gap, the reduction in the starting torque is more compared to the reduction in maximum torque. Why? Because the maximum torque is inversely proportional to leakage reactance, but whereas the starting torque is inversely proportional to square of leakage reactance. Is this point clear? Confirm me. Confirm me. So I'll write the point, then we can go for a break. With the increase in the air gap length, the reduction in starting torque is more compared to reduction in maximum torque. Is this point clear? Confirm me all of you. Confirm me all of you. Right. The next one is the effect of variable voltage and variable frequency on starting torque. We'll see that later, right? So shall we go for break? All of you confirm me once. Right, done. So I'll take, then I'll come back. Right. So I'm back. Right. So can you see me, all of you? Audio, video, and other things. Right. Right. So the next concept is the effect of variable voltage and variable frequency on starting torque. Right. Let me start that. Effect of effect of variable voltage and variable frequency on starting torque. Right. Let me take the torque equation. X2 naught square. You can see in this ns there is one f. In this x2 naught there are two f's. Altogether 3 f's. This is directly proportional to E1 square. This is directly proportional to V1 square. So from this, can I say starting torque is directly proportional to V1 square and inversely proportional to F cube. So let me take V1 is V, the supply voltage. From this, you can write starting torque is directly proportional to V by F whole square into 1 by F. Now let us see the three cases here. Whatever cases we have seen for maximum torque, let us see three cases. What is that? First one is we are varying the voltage magnitude, we are varying the supply frequency, but here V by F ratio is kept constant. You can see as V by F ratio is kept constant, the flux will remain constant. The flux will remain constant. If flux is remaining constant, then starting torque is directly proportional to V by F whole square into 1 by F. As V by F is constant, starting torque is inversely proportional to frequency. What do you mean by that? See, when I'm applying a voltage of V with a frequency of F, let the starting torque be T. Now, when I'm applying a voltage of V by 2, the frequency of F by 2, then what is the value of T start 2? So here you can see V by F ratio is kept constant. Then in this case, the starting torque is inversely proportional to frequency. As frequency is reduced to half, the starting torque 2 will be 2 times the previous torque. So like that, we can double the starting torque. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. Right? So please listen here. Listen here. If the question is like this, please get ready with the answers. Try to type the answers. If the question is like this, keeping the V by F ratio constant, keeping V by F ratio constant, if the supply frequency of an induction motor is reduced to half, the supply frequency is reduced to half, then what happened to the values of T max and T start? T max and T start. Please try to give the answer. T max and T start. T max and T start. So there is one more T max. Right. So very good. Right. T max will remain constant. Why? Because when V by F ratio is kept constant, then air gap flux will remain constant. Then the maximum torque, which depends only on that air gap flux, will remain constant. But here you can see, even if that air gap flux is constant, the starting torque is inversely proportional to frequency. As frequency is reduced to half, the starting torque will be doubled. Then what is the answer for this is that T max will remain constant, whereas the starting torque will be doubled. Starting torque will be doubled. I hope this point is clear. Right. Constant, right, 2T, correct. So this is one observation. Second case with respect to starting torque. Second case. What is that second case is? I'm not varying the voltage. I'm varying only the frequency. V by F ratio is not kept constant. Why? Because only voltage is, frequency is varied. As V by F ratio is not constant, flux will not remain constant. Flux will not remain constant. Then you can see starting torque is directly proportional to V square, inversely proportional to F cube. Then here, which parameter is constant for us? Voltage is constant. Then starting torque is inversely proportional to frequency. What do you mean by that? So if I'm keeping the voltage constant, if frequency is reduced to half compared to the previous one, then what happened to the value of T star 2? It is 2 cube into T, it is 8T. The value becomes 8T. So please remember, when a question is asked on such models, you have to see whether V by F is kept constant or only V is kept constant, right? If V by F is kept constant, starting torque is inversely proportional to frequency. If V is kept constant, starting torque is inversely proportional to cube of the frequency. You can see this is the answer. Is here confirming? Right. Case 3. Case 3. Right. Case 3. What is that case 3 means? Case 3 means here I'm varying the voltage, but frequency is kept constant. And V by F ratio is not constant. You can see as V by F ratio is not constant, flux will not remain constant. Starting torque is directly proportional to V square, inversely proportional to F cube. So this is constant. Starting torque is directly proportional to V square. If V2 is equal to V by 2 and if F2 is equal to F, then in this case, the starting torque 2 is equal to T by 4. It will be 1 by 4 times of the previous value. Is it clear? Confirm me. Is it clear? Confirm me. Right. So can I say, if anyone want to frame any question on the starting torque, we have seen all the models, right from the definition of starting torque, calculating a numerical to find out the starting torque, then the parameters by which the starting torque will be affected from the design scene. Then last one is the effect of variable voltage and variable frequency on starting torque. Is it clear? All of you confirm me once. Confirm me once. Right. The next performance parameter is, if you go back to my starting torque, maximum torque, I told you that by adding by adding some resistance in the rotor circuit, we may not improve or we may not increase the starting torque, but we can get the maximum torque at let me correct myself. So maximum torque is independent of rotor winding resistance, but the slip and the speed at which that maximum torque depends upon the rotor winding resistance. By adding some additional resistance in the rotor circuit, we can obtain that maximum torque at any value of slip. Is this point clear? Confirm me. Confirm me. Right. Now the question is, if I want to obtain the maximum torque at starting, what do you mean by that? See, whatever the numerical I have taken, what is the starting torque value of that motor? It is 27.64 Newton meter. This is the torque. Then what is the maximum torque of that motor? It can develop maximum torque up to 99.87 Newton meter. Say the load on the motor is very high, heavy loads. Then if I want to start the motor, the starting torque should be very high. But very unfortunately, the starting torque of this motor is very less. So if I want to start the motor with heavy load, I can improve the starting torque by adding some resistance. Now the question is, how much resistance I need to add in the rotor circuit to obtain the maximum torque at starting? That means I need to have this value of torque at starting. That means the motor has to be started with maximum torque at starting. Then what resistance I need to add, right? Let us see. Next performance parameter is the value of external resistance required in the rotor circuit to obtain maximum torque. To obtain maximum torque at starting, right? So let us see. Let SMT is equal to R2 plus R external by X2 naught. I need to obtain this maximum torque at starting. Then what is the value of slip at starting? It is 1. So the question is, what resistance you need to add in the rotor circuit so that that slip becomes 1? When that slip is becoming 1, then it says that the maximum torque is obtaining at starting. So from this, what is the value of R external I need to add? R external is equal to X2 naught minus R2. So this resistance you need to add external in the rotor circuit to obtain maximum torque at starting. So this is the equation for additional resistance to be added in the rotor circuit to obtain maximum torque at starting. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Then violate for the above problem the common data. For the above problem, calculate the external resistance required in the rotor circuit to obtain maximum torque at starting. So what is the value? So R external is equal to X2 naught is 0.85 minus 0.12. So it is 0.73 ohms. So this much resistance you need to add in the rotor circuit to obtain maximum torque at starting. Is it clear? Confirm me, all of you. Raise the hands. Right. So this is the fourth performance parameter. The next and very, very important thing is the gross mechanical power maximum. The last one is maximum internal mechanical power. See, whenever I'm talking about maximum torque, it is the torque after which the motor stops. Rated torque, it is the torque developed by the motor at rated current. Is this point clear? Confirm me. Is it clear? Confirm me. So, what is that maximum internal mechanical power? It is the mechanical power, or it is the rotor output power after which the motor will come to standstill position. What is that rated mechanical power? It is the mechanical power developed by the rotor with rated current. So whenever I'm using the terminology rated, means it is the current, it is the torque with rated current. It is the power with rated current. Whenever I'm talking about maximum, maximum is it is the torque after which the motor will stop rotation. It is the mechanical power after which the motor will stop rotation. So please remember that. Is this point clear? Confirm me. Is this point clear? Confirm me. So can we load the motor beyond the rated values? Yes. But if you are loading the motor beyond the rated values, the windings will carry the currents more than rated. The windings will be on heating. The temperatures will be more, the windings get heated up. And if you keep this load for longer time, the machine will get damaged. So that is the reason. So whatever that additional load you are placing on the shaft, more than rated should be only for short time. If you are keeping for the long time, the windings will get damaged. Then how to calculate maximum internal mechanical power? By the way, what is the equation we are having for internal mechanical power? If you remember, the internal mechanical power or the rotor output power is equal to 3. Already we have derived the equation. I2 square R2 into 1 by S minus 1. You remember this? All of you tell me. You remember this? Right. So I want this power to be maximum. I want this power to be maximum. For that, I write I2 mm square into R2 into 1 by SMM minus 1. What is that I'll give? So this one is current at maximum internal mechanical power, slip at maximum internal mechanical power, right? Internal mechanical power. So can I say like this? If I want to calculate this, I need these two. One is the current, the other one is the slip. I need these two. How to calculate current? So current already you know the equation. I2 mm is equal to E2 naught by square root of R2 by SMM square plus X2 naught square. So if I want to calculate this, what is required? SMM is required. Then how to calculate SMM means it is the slip at maximum internal mechanical power. How to find out this means by using maximum power transfer theorem, right? So what is that? I'll explain. SMM can be found by using maximum power transfer theorem. Then if you look into this power is dependent on which resistance? R2 into 1 by S minus 1. So if I want to apply this maximum power transfer theorem, the rotor circuit should be in such a way that which branch you need to show it as a load now, R2 into 1 by S minus 1. For that, what I'll do means, I'll consider this resistance, this equivalent circuit. R2 by S. I split this R2 by S into two parts. What are those? One is R2, the other one is R2 into 1 by S minus 1. So which branch I have to show it as a load means R2 into 1 by S minus 1. So I reshuffle this. If I do that, this is R2 jx2 naught. The other part is R2 into 1 by s minus 1. So I equate this impedance to the source impedance. If I equate this R2 into 1 by s minus 1, so this is equal to square root of R2 square plus x2 naught square. If I simplify, so from this I'll get SMM is equal to R2 by R2 plus square root of R2 square plus x2 naught square, and the speed is ns into 1 minus SMM. So tomorrow if the question is asked to calculate the maximum internal mechanical power, first you need to calculate slip. Once you are having slip, you can calculate current. Once you are having current and slip, you can calculate power. Like this, we can find out power. Then violate for the above problem, calculate 1. Get ready, SMM and the rotor speed at maximum internal mechanical power. Second one is the current at maximum mechanical power. Third is maximum internal mechanical power. Do it. I'll be waiting for that. Do it. I'm waiting for the answer. Oh, formula you want to show. Okay, this is the slip. You can see on the board slip. 0.12. Very good. Right? 0.12. Very good. What is the speed? 0.12. Excellent. 0.1226 generally. 0.12. So you write 0.1226 if I am correct. So SMM is equal to 0.12 by 0.12 plus square root of 0.12 square plus 0.85 square. If I'm correct, 0.1226. Then what is the value of current? Current is equal to E2 naught is how much? 76.96, or what is the value of E2 naught for this? 76 or 78? What is the value? Right, speed is 980. Absolutely. Speed is 980. Very good. Speed is 980. 1000 into 1 minus 0.1226. How much? Speed is not 980, I think. It is 858 point something, I think. 877.35, something like this. Right, done. Then what is the value of current? So what is the value of E2 naught? 76.96, I think. Then you substitute that and you calculate the current here. What is the current? 59.48. Very good. Current is 59.48. 48. What is the value of power? 3 into 59.48 square into 0.12 into minus 1. If I solve this, 9.08 kilowatts. So what is the maximum internal mechanical power means? 9.08 kilowatts. I hope it is clear, right? Done. You can check this, all of you. Right. So don't give the answers. Let me repeat once again. Repeat once again. Repeat once again. See, you should be in a position to understand this. See, if anyone questions you, or what is that you have learned as of now? What is that you have learned as of now? Means, what is that you have learned as of now means, see, if you are having a rotor equivalent circuit parameters, what are those rotor equivalent circuit parameters? R2, X2 naught, and E2 naught. These are the parameters. Is it possible for you to calculate the rotor current at any value of slip? Yes. How you are going to calculate the rotor current at any value of slip? E2 naught upon E2 naught by square root of R2 by S whole square plus X2 naught whole square. I can calculate the rotor current for any value of slip ranging from 0 to 1 if R2, X2 naught and E2 naught are given. Please confirm me. Confirm me. Raise the hands. Right. Can you calculate the rotor input power for any value of slip? Yes. 3I2 square into R2 by S. Can you calculate the rotor losses for any value of slip? Yes. Can you calculate the rotor output mechanical power for any value of slip? Yes. Can you calculate the torque for any value of slip? Yes. What are the formulas? If R2, X2 naught, E2 naught are given, if you want to calculate the rotor current at a particular value of S, S may not be given directly, speed also sometimes may be given, from that you can calculate S. So I2 is equal to E2 naught by square root of R2 by S whole square plus X2 naught whole square. Once you are having I2, you can calculate 3I2 square into R2 by S rotor input. 3I2 square into R2, the rotor ohmic losses. 3I2 square into R2 into 1 by S minus 1 rotor output power. Rotor input by omega S will give the torque at any value of slip. We can find out all these things, right? In addition to that, I can calculate the full load torque of the motor. I can calculate the maximum torque of the motor. I can calculate the starting torque of the motor. I can calculate the resistance for obtaining maximum torque at for the motor. I can find out the maximum internal mechanical power of that motor also. So with these three parameters, R2, X2 naught, E2 naught, with these three parameters for any value of slip, I can find out all these things. Is this point clear? Confirm? Is this point clear? Confirm? Right. So tomorrow, maximum of maximum, what they may ask means they may ask only these things. Why? Because for any motor, they may ask only these things. So only the thing is, if you want to calculate I2, you should know E2 naught. You have to see what are the various ways to have E2 naught, right? From that you can find out. Is this point clear? Confirm me, all of you. Up to here, okay, all of you confirm me. Right. The next one is some important relationships. Basing on this, many times in your gate examination, even in engineering service examination, we have some questions. Very, very important. Please go through this. Some important relationship. What is that? What are those important relationships? First of all, let me gather the equations which we have derived already. First one is, we have the electromagnetic torque for any value of slip ranging from 0 to 1. It is 180 by 2 pi ns. I call that 180 by 2 pi ns as K S E2 naught square into R2 by R2 square plus S X2 naught whole square. This is for any value of slip ranging from 0 to 1. This is already derived. Please confirm me. Confirm me. Confirm me. Right. So using this, we have derived the maximum torque. What is the formula for maximum torque? K E2 naught square by 2 x2. After that, we have derived the starting torque. What is the formula for starting torque? K E2 naught square into R2 by R2 square plus x2 naught square. And we have derived the full load torque. What is the formula for full load torque? K SFL E2 naught square into R2 by R2 square plus SFL into x2 naught whole square. I hope all this we have derived. Please confirm me. Confirm me. Right. Now what I want to do means I want to find out the ratio of this electromagnetic torque at any slip by maximum torque. Right, by maximum torque. Please see. Please see. I want to find out the ratio of, please see, the electromagnetic torque at any value of slip by the maximum torque of that motor. What is the formula we are having? K S E2 naught square. This is one important relation in induction motor. R2 by R2 square plus S x2 naught whole square by K E2 naught square by 2 x2 naught. So in this you can see KK, you can see KK cancels, E2 naught square, E2 naught square will cancel. Then if I simplify this, I'll have like this. What is that? It is 2 x2 naught R2. So this denominator will go as a numerator into S by R2 square plus S x2 naught whole square. Up to here, any doubt? Confirm me, clear? All right, done. What I will do means I'll divide with x2 naught square and I'll divide with x2 naught square. If I divide that, one x2 naught will get cancelled. If I simplify this, I'll have 2 into R2 by x2 naught into S by R2 by x2 naught whole square plus S square. Right? Please confirm if it is clear, all of you. Confirm. Right. And you know that the slip at maximum torque is equal to R2 by x2. So finally I can write the torque at any slip by maximum torque is equal to 2 into the slip at maximum torque into general slip by the slip at maximum torque square plus S square. So this is very important relation. Important relation. Is it clear? Confirm me, all of you. Is it clear? Confirm me, all of you. Right. How the question will be asked basing on this. Please see. I'm trying to see what are all the possible questions from this. See. So here, there will not be any information given about the excitation, voltage and frequency, the motor parameters R2, X2, nothing will be given. But what will be given me? See, I'm having a 3-phase induction motor. The maximum torque of that motor is 99.87 Newton meters, and it occurs when the slip is 0.41141. Then what will be the electromagnetic torque of that motor if the slip is 3%? Slip is 3%. So what is given? The maximum torque of that motor is given. The slip at maximum torque are given, and you are asked to calculate what is the torque at 3% slip for the same motor. No other parameters are given. Then how to find out? So I'll use this equation. What is that? So the torque at any slip, that is the torque at 3% slip, maximum torque is equal to 2 into 0.141 into 0.03 by 0.141 square plus 0.03 square. Then what is the torque at 3% slip, magnitude of torque at 3% slip? Can you please tell me? Can you please type the answer? Oh, I use some wrong units for current, so it may be printing mistake. Okay. So these are amperes. Thank you, Baba. Right. So what is the answer for this? Can you please tell me what is the answer for this? What is the answer for this? Can you please? 40.66 Newton meter. So this is the torque at 3% slip. You can see neither the motor parameters are given nor the excitation parameters are given. The only thing is the maximum torque and the slip are given, and you are asked to calculate what is the value of torque of the same motor if it is operating at a slip of 3%. So answer is 40.66. Is this point clear? Confirm, all of you. Is this point clear? Confirm, all of you. Right. So here there are three possibilities of framing a bit from this. Three possibilities. What are those three possibilities? See, three possibilities framing this bit. Three possibilities. See, these are all the questions which are being asked. I'm just giving the general layout. Three possibilities. So what are those three possibilities means? T max is given anyhow. T max is given. And this ST max, or what is the notation we have for this? Just 1 second. So this may be given indirectly or directly. What is the first one is given directly. Given directly. What is the meaning of given directly? I'll just frame the bit, from that you can understand. What is given directly? See, the maximum torque of a three-phase induction motor is 99.86 Newton meters, and it occurs when the slip is 0.141. Calculate the electromagnetic torque of the motor when the slip is 0.03. So in this, ST max is given directly along with T max, and you are asked to calculate the torque at 3% slip, right? So you can calculate the torque directly. Is this point clear? Confirm, all of you. Is this point clear? Confirm, all of you. Right. The second possibility is this ST max may not be given directly, but R2 and X2 naught are given. R2 and X2 naught are given. When R2 and X2 naught are given, how to calculate ST max? It is R2 by X2 naught. Once you are having R2 naught, you can calculate the torque at any slip. The question will be like this. A three-phase induction motor has a standstill rotor leakage reactance of 0.12 plus J 0.85 ohms with a maximum torque of 99.86 Newton meter. So what are the values given? R2 is given, X2 naught is given, and what else given? Maximum torque is given, and you are asked to calculate the torque at 3% slip. So for that you need ST max, you calculate ST max, then from that you can calculate the torque at 3% slip. Is this point clear? Confirm me. Confirm me. Right. The next possibility is neither the slip at maximum torque are given, R2 and X2 not are given. So here what is given means the rotor speed at maximum torque are given. Rotor speed at maximum torque is given. So if the rotor speed at maximum torque is given, how to calculate the slip at maximum torque? Ns minus Nr St max by Ens. Once you are having slip, you can calculate the torque at 3% slip. So what are the three possibilities? Maximum torque is given anyhow. Slip may be given directly. R2 and X2 naught may be given. Then the speed may be given. So using that you can calculate slip. From that you can calculate the torque at any slip. Is this point clear? Confirm all of you. Is this point clear? Confirm all of you. Right. So this is one equation. Equation 4 or 5? Equation 5. Then I'll be taking equation 6. What is that equation 6 and what is the importance of equation 6? So we have calculated the ratio of torque at any slip by maximum torque. I want to calculate the ratio of starting torque to maximum torque. If I want to calculate the ratio of starting torque to maximum torque, again you can take equation 3 and you can divide equation 2, then you will get the result. Or you can directly get from this equation. What is that? So you can see here TEM is the torque at any value of slip. I write TST. If I write TST in place of S, I have to write 1. So TEM is the torque at any value of slip. Then in place of the TEM, I'm writing T start. So in place of S, I have to write 1. Is this point clear? Confirm me. Is this point clear? Confirm me. So this is equal to 2 SMT by SMT square. So this is the ratio. I hope this relation is clear. Confirm me all of you. Confirm me all of you. Right. So what is the importance of this equation? Many times in GATE, engineering service, basing on this, there are many numericals. Not only on this, even from equation 5 also you have numericals. So what is the importance of this equation 6? Let me tell. What is that? See, if you just go for this performance parameter 4, what is that? Just see. So here the value of external resistance required to obtain maximum torque at starting. So here T max should be equal to T start, or in other way. So let me write the proper way of writing. T start should be equal to T max. So if I want to have starting torque which is equal to the maximum torque of motor, what is the resistance I need to add in the rotor circuit? X2 naught minus R2. Is this point clear? But it is not like in all the cases we need the total maximum torque at starting. We may not need the total maximum torque at starting. We may need something like 50% of maximum torque at starting. What do you mean by that? See, I'm having an induction motor. Let the initial load on the motor be 99.86 Newton meter. Initial load. The load on the motor is 99.86 initial load. So if I want to drive that load, what should be the starting torque of this motor? It should be same as 99.86. That means I need to start the motor with maximum torque. For that, what is the resistance I need to add externally? X2 naught minus R2. Is this point clear? Is this point clear? Right. But now the load on the motor is not like 99.87. The load on the motor is say 50 Newton meter. So when the load on the motor is 50 Newton meter, then I don't need maximum torque at starting. I need only 50% of maximum torque at starting. Why? Because the load on the motor is comparatively less. I don't need such high torques at starting. Comparatively, I need less torques at starting. How much torque I need? 50% of maximum torque at starting. Then in that case, what is the resistance to be added? Is this point clear? Confirm me. Is this point clear? Confirm me. All right. So I'll try to solve the problem. What is it? For the above problem, the common data. For the above problem, for the above problem, for the above problem, calculate, calculate the external resistance required in the rotor circuit, in the rotor circuit to obtain 3/4 of maximum torque at starting. 3/4 of maximum torque at starting. So I need to start the motor with how much torque? 3/4 of maximum torque at starting. So here let SMT is equal to R2 plus R external by X2 naught, right? For starting torque is equal to how much? 3/4 of maximum torque. Is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. Right, done. Then I'll substitute this here. So what is the value of T start? So it is 3/4 of T max by T max is equal to 2 SMT by SMT square plus 1. If I solve this, SMT square minus 8 by 3 SMT plus 1 is equal to 0. So here you'll get two values of SMT. Please tell what are those two values of SMT. What is the value of SMT? Can anyone tell? See, check for 0.03, torque is coming 0.407. You check once, right? So see, -1. So how come -1? 2.2 and 2.2 and 0.45. See, you are having two values of S here. One value is greater than 1, the other value is less than 1. So you know that what is the range of slip on an induction motor? It is between 0 to 1. So which one is having 0 to 1 range means it is 0.45. So what is the value of SMT? It is 0.45. So which is equal to R2 is 0.12 plus R external by X2 naught, 0.85. So from this, what is the value of R external? Can you please tell me? What is the value of R external? Can you please tell me? What is the value of R external? What is the value of R external? Why? Because you can see this. What is the value of R external? 0.2625. 0.2625 ohms. So this much resistance you need to add in the rotor circuit to obtain maximum 3/4 of maximum torque at starting. I hope this point is clear. All of you confirm with me. Confirm me, all of you. Right. So this is something about your some concept, but still it is not over. We have few more points to be discussed. So as this is the time for doubt discussion, so I'll stop for today. So this class, so we'll continue with the doubt discussion. Just give me 1 minute time and get that earphones. Right, I'll come back. See, sir, how many days are required for completing induction motor? After tomorrow, 10 more hours is required. So we'll see. Sir, induction motor is a motor at which we are not supposed to load at starting. Then at no load, the rotor speed is ns, no sir. How starting s is equal to 1? See, I don't know what is your question at all. See, I never said that the induction motor should not be, we are not supposed to start the motor with load. See, if you take this numerical, what is the starting torque of this motor? The starting torque of this motor is 27.67 Newton meter. So the maximum load what you can put at starting is around 27 Newton meter. And if the load is less than 27.64 Newton meter, the motor can start rotating. It will rotate, right? So please remember that it doesn't mean that with the load, the motor cannot start. If the motor is able to produce the required torque to drive the load, it will start rotating. Don't worry with that. So can you please tell me the difference between full load torque and maximum torque? That was already explained to you. Go through the notes. If there is a load change, is there any automatic or manual change in external resistance? So external resistance has to be changed always manually. Please remember that. How many marks for induction motor in gate? The induction motor marks will be 2 marks 1 and 1 mark 1. Maximum 3 marks will be there, right? Please. Now let us see the question and answers. Right? Hand raise students. Right. Meena.
Hello, sir.
Hama, please.
Sir, last 6 point lo 3/4 of starting torque అని చూడండి సార్, అది కొంచెం ఎక్స్ప్లెయిన్ చేస్తారా సార్?
See, it is not like 3/4. The thing is, I am having a slip ring induction motor, right? So that slip ring induction motor starting torque should be 3/4 of maximum torque, right? I want to start the motor whose starting torque is equal to 3/4 of maximum torque. That means the starting torque should be increased to how much value? 3/4 of maximum torque. So if you want to raise the starting torque to 3/4 of maximum torque, what is the value of additional resistance you need to add in the rotor circuit? How much resistance you need to add? 0.2625. Is it clear, ma?
Okay, sir. Thank you, sir.
Is it clear, ma? Any doubt more? So
No,
tomorrow they may ask, what is the resistance to be added for obtaining 80% of maximum torque, 70% of maximum torque? Like that, the percentages may be differed, but the procedure which you need to follow should be like this. Is it clear, ma? You follow this. Okay?
Yes, sir.
Right, ma, right.
Thank
Any
you,
doubt?
sir.
Right, ma. Yeah, Imtiaz Pasha.
Good evening, sir.
Good evening, Baba.
Sir, for scroll induction motor and slipping induction motor, the maximum torque will be independent of the resistance, sir.
So you are not supposed to talk about squirrel cage or slip ring. So whenever we are, let me finish your answer, then I'll come back to your question. See, your question is, for squirrel cage and slip ring, maximum torque is directly proportional to resistance. See, the question is, it is not slip ring or squirrel cage. So the maximum torque of an induction motor is directly proportional to rotor winding resistance. It may be a squirrel cage or it may be a slip ring. Now your question.
Okay. Sir, maximum torque is proportional to the E2 square by 2x2, no, sir.
It is directly proportional or it is
proportional to okay. For normally Scroll gauge motion is used for the heavy load now, sir, compared to the scroll gauge induction motor, because of the full load torque is equal to approximately equal to maximum torque by 2.
See, who told that relation? Full load torque is, see,
So approximately you said no, sir. Until 55 point we get the full load torque, maximum torque we get the 99.87.
it is not like every motor. It is something like the design, right? So if you take any induction motor, the full load torque, if it is a 50 Newton meter, the maximum torque of that motor will be under the 100 meter. It is like this. The full load torque and maximum torque ratio will be around 1/2. Now, what is your question?
Generally, the scroll gauge induction motor used for the heavy load, no, sir.
Squirrel gauge induction motor is not used for heavy loads. The squirrel gauge induction motor is used for light loads and it can be loaded heavily.
वही sir. मतलब from starting to up to end they can use for the heavy load.
So light load to heavy loads. Yes.
Heavy load.
Hmm.
But sir, one more doubt is there. You said starting we can use the maximum torque.
Yeah, by adding some additional resistance, the starting torque can be raised to maximum torque value.
Sir, if we use the starting at the maximum, the resistance of the winding will be increases, no, sir.
Definitely, the resistance will be more, ohmic losses will be more, heating will be more, but it is only for short time. So whatever, once the motor starts picking up, we don't keep that resistance. Why? Because once the motor starts picking up, what happened to the rotor frequencies? Decreases. Then what happened to inductive nature of the rotor circuit? Decreases. Then by default, the rotor circuit resistance will start dominating. The torque will increase. So once the motor starts picking up, you are not supposed to keep that high resistance in the rotor circuit. Once the motor starts rotating, you have to cut down that additional resistance. It is only for starting purpose, not to keep permanently.
Okay, sir. It's a transient state like that.
Yeah, it is only for transient conditions. Still, it reaches to full load value. Understood?
Okay. Yes, sir. I got.
You got it? Right.
Yes, sir.
Right. Sai Charan Reddy.
Hello, sir.
Hama.
Sir, I did not understand that full load torque and the maximum torque you told the difference, no, sir, before explaining this.
See, I told you that full load torque is the torque developed by the motor with rated current, the safest currents, right?
Yes, sir.
You are clear with that?
Yes, sir. Yes, sir.
Maximum torque is the torque after which the motor will be stopped. Is it
Yes,
clear?
sir. Okay, sir. Okay, sir.
Individually. Now say I have started a 3-phase induction motor without load.
Yes,
Okay.
sir.
Then what will be the current drawn from the supply? Very less.
Yes, sir.
Now you start loading the motor. When you start loading, when you are increasing the load on the motor, what happened to the current drawn from the supply?
Increases.
Now a stage has come, the windings are carrying the rated current. Then what is the torque developed by the motor?
Full load torque.
Full load torque. But by overlook, without looking into the winding currents, you started still loading the motor. Will it rotate?
Yes, sir.
But what will be the winding currents?
Increases.
More.
More than
Then
rated.
you can see that smell will be coming out of the machine, but still the motor will be rotating.
Yes, sir. Yes, sir.
So indirectly it says that the motor is
Motor
overloaded.
is overload.
Overload. And if you keep that load for long time, then what happened to the windings?
They'll damage.
Damages. But now what happened means you go slowly increasing the load, not keeping the load for long time. Slowly increasing. A stage has come, it has crossed the full load and it has reached the maximum load. Then obviously what happened? It will not further rotate. It will finally stop.
Okay, sir.
Now you understood the difference between these two now?
Yes, sir. Yes, sir.
Now you are
Sir, can we tell that this maximum torque will be in unstable region? Can we say like that?
it is not unstable region, it is a stable region only, right? So it is overload between full load and maximum, the motor will rotate. When the motor is rotating, means it is supplying the required load torque, but with the sacrification of that heating. So it is
Okay,
supplying the
okay. Yeah,
required
yes,
load
sir.
torque.
Yes,
It
sir.
is not like unstable.
Yes,
Understood?
sir. Okay, sir.
But the windings are carrying high currents. Because of
Yes,
that, the
sir.
windings may get damaged. If you keep for long time, please
Yes,
keep
sir.
that in mind.
Okay, sir. Okay.
Understood?
Yeah,
Understood?
Yes, sir.
Any
Yes,
more
sir.
doubt?
No, sir. No.
Right. Bhavani. Bhavani. Dupati Bhavani.
గుడ్ ఈవినింగ్ సార్.
Good evening, ma.
సార్ మీరు చెప్పారు కదా సార్ స్టార్టింగ్ సారీ
చెప్పు నాన్న.
సార్ స్టార్టింగ్ మాక్సిమం టార్క్ వచ్చిన తర్వాత బియాండ్ మనం వెళ్తే మోటార్ స్టాప్ అవుతుంది అన్నారు కదా సార్.
అవునమ్మా.
ఒకవేళ ఇప్పుడు మనకి స్టార్టింగ్ టార్క్ ఈజ్ ఈక్వల్స్ టు మాక్సిమం టార్క్ ఉన్నప్పుడు ఆ మోటార్ కి స్టార్టింగ్ లో మనం లోడ్ వేసిన తర్వాత మళ్ళీ ఇంకా లోడ్ ఇంక్రీజ్ చేస్తే స్టాప్ అవుతుందా సార్?
అంతే కదా. సే ఫర్ ఎగ్జాంపుల్ the maximum torque of that motor is 100. Assume that. Okay. So you are obtaining the torque at starting only.
Yes.
Okay. So what is the load it can drive? 100 Newton meters. Is it clear? But very unfortunately, at starting you are placing 200 Newton meter weight. But what is the maximum torque of that motor?
100.
Will it drive that load?
No.
No. It is something like this. You take a railway coolie. Okay. So he has not taken any food, any stuff. Then what is the weight he can carry? Is 50 kgs.
Okay.
Then he has taken some dry fruits and other things. So with the additional energy, he can carry 100 kgs maximum. So what is the maximum weight he can carry with the dry fruits and other things? 100 kgs. So
100 kgs.
if you put 100 kgs, then he can carry that 100 kgs. But it doesn't mean that even after taking dry food or other, if you put 200 kgs, will that fellow carry that 200 kgs?
No.
So here also, even if you are adding resistance and if you are obtaining the maximum torque of that motor, what is the load you can apply at starting? Only that maximum torque load you can apply. Beyond that, the motor cannot rotate. Is this point clear?
మనం స్లోలీ ఇంక్రీజ్ కూడా చేసుకోలేము కదా సార్ ఓవర్లోడ్.
No. Why? Because maximum torque is reached. So if see, I'll tell you one thing. You take the maximum torque as 100 Newton meters. Okay. So initially you are applying 10 Newton meters.
Okay.
What is the initial load at starting? 10 Newton meters. The motor starts rotating, right? Now you are increasing the load slowly up to 100. Then up to 100 it will rotate. But if you are loading beyond 100, will it rotate? No. It will come back to standstill position.
ఓకే సార్. సార్ మీరు ఒకటి పీక్ టార్క్ దగ్గర ఒకటి ఎగ్జాంపుల్ ఇచ్చారు కదా సార్, లైక్ 0 to 1 వరకు వేరీ చేసి టీఈఎం క్యాలిక్యులేట్ చేస్తారు. జస్ట్ అప్రాక్సిమేట్
క్యాలిక్యులేషన్ మెథడ్.
ఎస్ సార్. మాక్సిమం టార్క్ రీచ్ అయింది కదా సార్, దాని తర్వాత స్లిప్ ఇంక్రీజ్ అయ్యే కొద్దీ మళ్ళీ జీరోకి రావాలి కదా సార్?
జీరోకి రాదు. స్టార్టింగ్ టార్క్ 1. స్టార్టింగ్ టార్క్ 0 కాదు కదా. The starting torque of this motor is not 0. So I'll draw the torque slip characteristics. The starting torque is not 0. If the starting torque is 0, the motor cannot start rotating. Is it 0? The starting torque is 0?
No.
So no. You have calculated already the starting torque value, correct?
Yes sir. Okay, I understood.
Okay ma.
Okay sir, done sir.
Right ma, right.
Thank you sir.
Right Nana, right. Raviteja.
Good evening, sir.
Good evening, Baba.
ఇక్కడ స్లిప్ ఫర్ మాక్సిమం మెకానికల్ ఇంటర్నల్ పవర్ కి అది అర్థం కదా సార్ నాకు అక్కడ.
రైట్, I'll go back. So this power is dependent on which resistance?
R2.
Not R2. R2 into 1 by S minus 1.
Okay.
If this is consuming maximum power, this R2 into 1 by S minus 1 is consuming maximum power, then this power will be maximum or minimum?
maximum.
Right. So if I want to have maximum power for this R2 into 1 by S minus 1, so we have modified this rotor circuit into such a way that this R2 into 1 by S minus 1, we are showing it as a load now, correct?
Sir.
So for that R2 by S, we are splitting into two parts, R2 and R2 into 1 by S minus 1. Then by applying this maximum power transfer theorem, what is that maximum power transfer theorem says that if this load impedance is equal to source impedance, the power will be maximum. The same thing I have applied here. Is this point clear?
Okay,
So
sir.
this is which theorem? Maximum power transfer theorem. Using
sir.
that we have calculated. I wrote already there. Can be found using maximum power transfer theorem. Understood? Ravitej?
Understood.
Right.
సార్ ఇంకొకటి ఇక్కడ
Audible?
మీరు మాక్సిమం టార్క్ అనేది రెసిస్టెన్స్ మీద ఇండిపెండ్ అవుతున్నారు కదా సార్.
Yes, maximum torque is independent of resistance. Correct.
మరి ఇక్కడ మాక్సిమం స్లిప్ అనేది R2 మీద డిపెండ్ అవుతుంది కదా సార్ ఇక్కడ.
The slip at maximum torque depends upon R2. Correct.
అంటే ఈ రెండింటికి రిలేషన్ ఉండాలని.
ఉండదు కదా, స్లిప్ వేరు టార్క్ వేరు.
ఓకే సార్.
Slip is the value at which that yes, the torque will be there. Understood? So in between 0 and 1, the maximum torque can be at any value of slip. Right? If you just, I am assuming that you know the torque slip characters. Just assume that.
Okay.
Ilaga. So at any value of slip, I can have maximum torque. So like this. Anyhow, I'll draw this in the coming days. Don't worry. Understood?
Okay.
Slip
Okay,
will be variable, but maximum torque is independent of resistance. Understood?
Understood, sir. Thank you,
Right.
sir.
Right. Pratyush.
Good evening, sir.
Good evening, Baba.
Sir, when I was solving the questions, I have came across this, sir. Sir, he said that semi-closed sort, by using semi-closed and closed, we can improve efficiency, sir. He said. Sir, I am assuming that in case of semi-closed and closed, the leakage flux lines are more, no, sir.
Say the leakage flux lines are less in open slots, right?
Yes, sir.
Then compared to semi-closed, they are more. Compared to closed, they are high. Okay.
Yes, sir.
So
Yes,
in which slot the leakages are more?
Closed slots, sir.
Okay. Now your question.
My question is, if the leakages are more, the power factor will be poor, no, sir.
Yes, if the leakages are more, the power factor will be poor. Correct.
Sir, if the power factor is poor, we will discuss about efficiency in the random conditions only, no, sir.
See, one thing. What is the question of efficiency? The power which is coming to the motor and the power which is converted into mechanical power. The
Yes,
ratio of that power to this power defines efficiency, correct?
Yes, sir.
But because of the leakages, the amount of power which is being drawn from the source is getting reduced. The
Yes,
input
sir.
power itself is getting reduced.
Yes, sir.
Then with respect to that, we are not supposed to talk efficiency, na? So these leakages are not having any losses. They are reducing the power.
Okay, whatever the power drawn, with respect to that only we have to talk efficiency.
Correct. Understood now.
Yes, sir. Sir, I have another doubt, sir. Sir,
you can ask any doubt, no issue.
Sir, we are talking about only rotor design parameters with respect to torque with respect to rotor design parameters, no, sir.
As of now, rotor. After that, we'll include stator and we calculate everything.
ఓకే సార్. అంటే నా డౌట్ ఏంటంటే సార్, ఇప్పుడు ఒక మిషన్ కి స్టాటర్ లో ఓపెన్ స్లాట్స్ ఉన్నా దానివల్ల మనం టార్క్ ని, అంటే టార్క్ ఎఫిషియన్సీ టార్క్ కంపేర్ చేయొచ్చు సార్. అంటే ఒక దానికి స్టాటర్ లో ఓపెన్, ఇంకో దానికి స్టాటర్ లో క్లోజ్ ఉన్నాయనుకో.
యా, వి కెన్ డూ ఇట్, నో ప్రాబ్లం.
ఓకే సార్. సార్ లాస్ట్ వన్ సార్. సార్ ఇప్పుడు VBF కాన్స్టెంట్ మెథడ్ లో స్లిప్ అట్ మాక్సిమం టార్క్ ఈజ్ ఇన్వర్స్లీ ప్రపోర్షనల్ టు ఫ్రీక్వెన్సీ, నో సార్?
ఎస్ అమ్మా.
సార్ ఇప్పుడు ఫ్రీక్వెన్సీ కనుక తగ్గిస్తే స్లిప్, అంటే ఎక్కడైతే మాక్సిమం టార్క్ అక్కడ అవ్వాలో స్లిప్ అనేది తక్కువ ఉంటది కదా సార్?
అంటే ఫ్రీక్వెన్సీ డబుల్ అవుద్ది, పెరుగుద్ది కదా.
అంటే f/2 అయినప్పుడు 2/f, అంటే స్లిప్ అనేది 2/f అవుతుంది కదా సార్? అంటే
2s అవుద్ది.
ఎస్ సార్. అంటే
డబుల్ అవుద్ది.
ఎస్ సార్, డబుల్ అవుద్ది. అంటే రిలేటివ్ స్పీడ్ తక్కువ ఉన్నట్టే కదా సార్?
రిలేటివ్ స్పీడ్ ఎక్కువ ఉన్నట్టు కదా. అంటే స్లిప్ పెరిగిందంటే స్పీడ్
తగ్గుతుంది.
రిలేటివ్ స్పీడ్.
ఓకే సార్.
అండర్స్టూడ్.
ఎస్ సార్.
అర్థమైందమ్మా?
ఎస్ సార్. అంటే ఇప్పుడు మనం ఫ్రీక్వెన్సీ వేరీ చేస్తూ ఒకవేళ రిలేటివ్ స్పీడ్ తక్కువ ఉంచితే మనకి అంటే అది అడ్వాంటేజే కదా సార్. ఎందుకంటే రిలేటివ్ స్పీడ్ తక్కువ ఉంటే కరెంట్ అనేది తక్కువ ఉంటది. సో కరెంట్ అంటే అక్కడే మనకి మాక్సిమం టార్క్ వచ్చేసినట్టయితే మెషిన్‌కి ఎలాంటి ప్రాబ్లమ్ ఉండదని చెప్పొచ్చా సార్?
ఇప్పుడు V/F కాన్స్టెంట్ అంటే ఫ్లక్స్ కాన్స్టెంటా కాదా?
కాన్స్టెంటే సార్.
ఫ్లక్స్ కాన్స్టెంట్ అంటే కరెంట్ కూడా కాన్స్టెంటా కాదా? సో whenever you are keeping V/F ratio, remember that the current is remaining constant. There is no change in current.
ఓకే సార్.
Understood? So
Yes,
at
sir.
maximum there is no change in current. So before V/F, even after V/F, the current will remain same. There is no change in current.
ఓకే సార్. ఓకే.
Understood?
ఎస్ సార్. థ్యాంక్ యూ సార్.
Right, Amma. Right. I'm waiting. Anyone can raise the questions? Still anyone? Right. Anyhow, I'll stop for today. No one is raising.